Okay, now we're recording, and let me go to current slide. If you don't do things in a certain order, you lose the ability to do it. For some reason, opening the PowerPoint will block my ability to start the recording, so I have to wait and start the recording before I can open PowerPoint. I can have it set up to open, but I can't open it. And now it's not doing anything but sitting there shaking. Another, probably not going to be 2 minutes, but there it goes. All right. Now, any questions? Well, okay. We did this slide last time, okay? But then the next part of the slide is the picture, okay? Now let's go back and say this formula illustrates this bullet point. The distance, nope, sorry. Where is it? Yeah, distance is proportional to the time squared. That's exactly what this distance is proportional to time squared. Proportionality constant is 1/2 a. And a is usually the acceleration due to gravity, which we usually call g, and g is usually 9.8 meters per second squared negative, or negative 32.2 feet per second squared. So that's what this figure, this function illustrates. Okay, we're going to see a pictorial of it later. This, though, indicates this. The speed increases linearly with time. You double the time, you double the displacement. Well, no, I'm sorry, this is distance. Where is the time one? There it is. Oh, I was on the wrong slide. Okay, there it is. This is the one that speed increases linearly with time. You double the time, you double the distance. Okay? I mean the speed. Quadruple the time from 1 to 3 seconds, you triple the speed. Quadruple the time from 1 second to 4 seconds, you quadruple this. 4 times 9.8 is 39.2. So the speed increases linearly with time. Here's the formula for it. Final speed is equal to a times t. Speed increases linearly with time, direct proportion, proportionality constant, your a, acceleration. Usually on Earth, 9.8 meters per second squared, and that's why these things are all in meters. Okay, multiply that by 3, and you get 29, 9.8 meters per second. Now this 9.8 is not just this 9.8, okay? It is the same number, okay? But you see, if you took this formula here and moved it up here, V final would be A 9.8 times 1. And that gives you this. This 9.8 is meters per second squared. They didn't put the units down. They're open for a $6 billion error here, okay? That should be meters per second squared. This should be seconds. Cancel one of the seconds out, and you get meters per second. That's where the 9.8 up here comes from. That's not the same as this one. This is the acceleration, 9.8 meters per second squared. That's the speed, 9.8 meters per second after 1 minute. And you put that same t in any of those places, and that's how you get your speed variation. Okay. And this is also the one that we've had okay, here. It varies, it's the up and down trajectories exactly mimic one another. So if this were falling down here and happened to hit an exactly elastic surface that sprung it back at exactly the same velocity, then it would be losing speed at that and getting closer and closer together until it just barely touched up here, and then gravity starts acting again and pulling it back down. That's what they mean by, come on, there it is. Trajectories exhibit up and down symmetries. Now here's someone trying to get in. I think it's Daniel Ruiz. Okay, let me get him, Daniel, here. Okay, welcome, Daniel. Had you come earlier and then tried again? Daniel, you had? Sorry about that. I was here early, started Zoom, and Zoom sat connecting for 2 minutes till it went to the next screen and went there connecting for another 2 minutes, and then when it finally, okay, but you're already in. That's, I don't know. I think too many people are on it. Let's see who this is. Rodrigo is here. Um, and so I actually finished the treatment a little early, had time to eat lunch and then get up here, and also did some things for class today. So I don't, yes. What is the game plan today? We are getting a test afterwards. No, not necessarily. Depends on how far we go in chapter 2. We have quite a bit to go yet. We're still in motion. We're going in one dimension. This is horizontal motion we've already done, vertical motion we're on now. 2.5 is compound motion, when you go up and down like these baseball hitters hitting their home runs. That follows a parabolic curve, the compound motion. Okay, then we have the 3 laws of motion, and they have sections on each one of those with several examples for a lot of them. Then we do weight and mass, and when we finish that with some examples, we go to momentum. And momentum has several examples. Okay, then we do forces in circular motion, which involves and then moves on to, it has several problems. Then we have Newton's law of gravitation, which has a couple of problems, and then we do applications of our satellites and weightlessness. There aren't any real problems associated with those. That is about 20 pages from where we are now. Okay. No, no. We will do a lab, but we won't be finished with the chapter. There will be a third lab on Tuesday. See, last time we did 10 pages. So I think if we do about 10 pages again, we'll do the second lab. See, unlike Physical Science 1, where every chapter had 1 lab and 1 test, in this one, these are long chapters. They have several labs and then only 1 test at the end. So we'll do actually more labs, I think, than we did in 111, but we'll do fewer tests than we did in chapter 11. I mean, Physical Science 111. Okay? Does that make sense? Okay. Uh-huh. Okay. Okay. Hang with it. Ask yourselves sort of the questions I'm trying to ask you, to start thinking through the problems, and after a while they'll become old friends. You move to a new neighborhood, you don't know anybody, you don't know what they're thinking, they don't know how they're looking, so you're a little intimidated, but after a while you get to know them and they become good people. So that's how it's going to be here too. Okay, 2 people are waiting. Let me get them in. Oh, Daniel must have gone back out. And Dre is here. So Daniel's coming back, Dre's coming in, and we are recording. I had marked Dre present when Valerie came in, so now I've marked Valerie present when Dre came in, and Daniel was already in, and I've got him. No, goodness gracious, I've messed up here. I put him under Sharonica. So Daniel is here. Haven't seen Sharonica yet. She turned in some work, or a student syllabus acknowledgement page, so I had to count her as present, but she's never been to class. And we've already had 2 labs, 1 test, and we've got another couple of, we're going to have another lab today. And now I've got Rucker in the waiting room, but it won't give me permission to let him in. There he goes. Okay. Boy, Zoom or the internet or something is really wacko today. So Rucker is here. Okay. No, you're not muted. Well, who is that Valerie? No? Yeah. It's okay. It's all right for you to laugh. That's fine. Okay. Tobias isn't muted, but he's not making any noise. So we should have 9 students here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Got it. Okay. Now, it doesn't matter. You're not making any noise, so it doesn't bother me at all. Now, if someone comes in and starts yelling at you, you might want to mute them out. So, or if you start yelling at somebody, you might want to mute them out, yourself out. Yeah. So we've already defined free fall. We did that last time. Falling under the influence of gravity without air resistance, which is not reasonable, except at slow speeds, air resistance is negligible because the air resistance is proportional to the square of the speed. And if the speed's very low, the square of the speed is very, very low. So for very low speeds, that is a legitimate assumption. Okay, we've already seen that distance is proportional to time squared. The formula showed that. I can't get it to advance. It still won't advance. Let's try it this time. Yeah, that formula shows distance is proportional to time squared. Speed increases linearly with time. Oh wait, let's go back. This illustration shows that distance is proportional to time squared. You double the time, you quadruple the distance. Triple the time, you 9 times the distance. Quadruple the time, 16 times the distance. Okay, so distance is proportional to time, but speed varies linearly with time. Speed is equal to AT, direct proportion there to time to the first power. So you just multiply 9.8 meters per second squared, that's your acceleration, A or G, by 1, you get this one, by 2, you get that one, by 3, you get this one, and by 4, you get that one. Varies directly, linearly with time. The trajectories exhibit up and down symmetries. If you were to throw a ball upward from the street here at whatever its maximum speed is, 40, 45, 50 miles an hour, throw it upward, then it would be at this point in 1 second, that point in 2 seconds, that point in 3 seconds. It would be at that speed, that speed at those times. It would be at this distance in those times. Now, you'd have to throw it up with an acceleration of 9.8 meters per second squared at an initial speed of, say, 40 or 45. That's the wrong slide. Okay, with initial speed of 40 to 45, throwing that up, then it would be at that distance from the top. Now, you start from the bottom. Your D0 here is whatever the height of the building is. So that's where you throw it from. It would be at this level in 4 seconds, that in 3. So it shows, and then when it gets to the top, it stops and starts falling down at this same relationship. Now, the key here, the acceleration is the same for all objects. Here was the acceleration that influenced the displacement. There was the acceleration as it influenced the velocity, and it's always 9.8 meters per second squared downward. Okay, now this was the example I told you about when I dropped the 1,000 kilogram, 1 kilogram mass, which is 1,000 grams, and the 1 gram mass from the high up as I could get in the B building there on the Bessemer campus, 3rd floor window there, and they all both hit at the same time. Galileo did this with rocks. He had his assistant go to the Leaning Tower of Pisa, that was his hometown, and got on the downward part of the lean, dropped a heavy rock and a lighter rock. They fell at the same rate, the same speeds, the same distances. He refuted Aristotle's claim that heavier objects fall faster than lighter objects. Sure, if you'd have been standing under that heavy rock when it hit, or the lighter rock when it hit, you would say, yeah, that heavy rock was moving faster. No, they're doing the same speed, but the heavier rock had more mass, and we haven't talked about that yet. That would be what you were noticing, and that's probably what Aristotle was observing, and he just called it the wrong thing. He said they fall at different speeds. Okay? That's your falling objects, one-dimensional motion downward. Okay? Now, where are we here? Let's see what the next slide is. We're going to go to compound motion. Before we do, we were supposed to have had the Summer Olympics this past summer. Of course, we didn't with COVID. If we ever get to play those Olympics, next summer, the following summer, whenever, one of the sports there is illustrated on page 37, this bicycle racer's edge. And if you've watched those things, someone moves out into the lead early in the bicycle race, and everybody else gets as close to him as they can. Does anyone know why? Yes, that's a very good word for it. They draft on him, or and that's what they call it. They call it in car racing, if any of you are the NASCAR fans. Actually, runners do it for long distances. And sometimes even the horses do it in horse races. The jockeys do it there. Because here's the deal, folks. And what's more, we weren't the first to come up with that, meaning mankind. Okay? If you've ever watched geese flying on their long transits, either north to south in the wintertime or south to north in the summertime, how do they fly? In a V-shaped pattern. Because that first goose up there at the point is taking on a lot of air resistance as he or she is flapping his or her wings, and the others are drafting on them. That's why they get in that V shape. And when that one gets tired, that goose drops out and moves down and gets at the back of one of the V's. And that V moves up and the other one takes it. And they keep alternating that as long as they're flying. They knew about it in nature probably long before we knew about it here. Why? Because there's always air resistance, okay? Bicycles are going usually, now some of those races, they go so slowly, I don't understand those races at all. But the real races, the foot races, the horse races, the bicycle races, the speed skate races, the long distance one, not the short one, not the sprints. Sprints, you want to get ahead and stay ahead. But when they're a little bit longer distance, then whoever goes out in front most of the time is going to be sacrificed to a member of his team who's going to drag on him or draft on him. And that happens on the interstate too. If you ever get behind a really big transfer truck and he's over in either the right or left lane from you, if you get sort of in his draft, if he's already going the speed limit or greater, you get in his draft, you're going to get a lot better gas mileage, certainly than he will, of course, but than you would if you hadn't been drafting on him. Don't get too close. Don't do it behind him. Do it in the lane next to him like those smart geese do, okay? And draft on them that way. Because there is, at higher rates of speed, there is air resistance, and you can't go by this. So that's what the blurb's talking about there, top of page 37. Okay. Then, on the top of 38, there's another closer look, and there are two meanings for free fall, and I'll let you read that. Skydiving, well, I guess I'll go on and do it. What free fall is in skydiving is you're coming down without the aid of the parachute. They call that free fall. Is that really free fall? I hope not. Okay, I hope that these people aren't dumb enough to do that. The closest you could get to free fall then is if you stood erect in the air, maybe put your hands above you like this, pointed your toes, and came down just as fast as possible. That's not how they do free fall in skydiving. What they do, they spread out to get just about the most surface area they can. As they pick up speed, they reach their terminal velocity, which we've talked about before. That's what threw Aristotle off. He didn't understand that about air resistance. But they do that and reach a terminal velocity, still falling, but not accelerating in the fall. And then when they get to a certain distance above the earth, they pull the ripcord, and then they've just increased their surface area big time. So now they slow down to that terminal velocity, which is much, 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 much less than otherwise. So that's the sports definition of free fall. So that's at the top there. You can read that. If you find anything in any of those that sound like it would be a good paper topic, go for it. Okay. Now, let's do examples 2.7, and it has two solutions. I'm not sure I'll do both of them. I'll do the one that makes the most sense, but if it makes sense, I'll do them both. A rock that is dropped, okay, into a well, hits the water 3 seconds later. Ignoring air resistance, how far is it to the water? So here you are. If I could get my pen to show up, I thought I had it. Nope, wrong end of the pen. Okay. All right, here you are at the wishing well. Okay, here's the ground level, somewhere around there. And here you are standing here. And you have long arms, don't you? Okay. Okay. All right. And you have a rock here. And the well goes deep. I didn't leave enough space for it. But somewhere down here, you have the water level. Okay. There's your well. If I could draw, I would draw the bucket up here and the pedestal. I can't draw, so you have to imagine that part. Imagine that's a well. Okay. Now, we know the delta T from the time you drop the rock until it hits the water is delta T. The time interval is 3.0 seconds. Boy, exact to the nearest tenth of a second. Okay? Ignoring air resistance, how far is it to the water? So we're looking for what's the distance to the water. Well, is there any formula or equation that relates distance to time? Please say yes. D is equal to, now, before we answer that question, let's think about what it says. A rock is dropped from up there. Dropped. You're holding it at one time, you just release it, and it falls from there. What was its initial velocity? Where did my pen? There it is. Okay, right here. VI is equal to the word dropped connotes initial velocity is 0. If you had thrown the ball into the well, that's a different story. Your initial velocity is not 0. If you had thrown the ball up and it came back down and fell into the well, you'd have had a different initial velocity. That's not what we've got here. Dropping is just releasing, giving it no initial velocity except that pulled by gravity, so its initial velocity is 0. Okay, now, since it says how deep is the well, and that's what we're measuring here, we're assuming there that our, where is my pen now? Oh, it's way down there. Okay, we're assuming here this is D0, your initial position, and that's also 0. How deep is the well? That's going to give you this D. So now that we have initial velocity 0, I've used different terms here. Let's call this D sub I. Come on, pen, where are you? Can anyone see it there? There it is. Okay. DI is equal to 0. So therefore our formula is 1/2 GT squared, or delta T squared. Okay? So that's going to be 1/2 of 9.8, we're assuming we're in metric system, meters per second squared times 3.0 seconds squared. Okay, so this will be, I'm going to take 1/2 of 9.8 just so I don't have to carry that around anymore, and make that 4.9 meters per second squared times 3.8. Remember, please excuse my dear Aunt Sally. We've got to exponentiate here before we multiply there. Now we can multiply these out front because there's no exponentials, but right here we have to exponentiate. 3 squared is 9.0, but you also square the units, and that will be seconds squared. Well, what happens here? Your second squareds go out, okay, and that gives you 4 times 9.0, 4.9 times 9.0, which I think is about 30. Let's see, that's 1. No, that's about 43. 36, yeah, about 43.1 meters. Okay, now hold on a moment here. Our speed was given to 2 digits. Time was given to 2 digits. We only used 2 digits in our acceleration, so we can only do 2 digits here. So this is about 43 meters. Now that sounds too deep, is it? They rounded to 44. How in the world did they do that? Did I do my math wrong? Yes, I did. That's 44.1. Sorry. I was doing it in my head, and my head is not really with it today. I think what I'll do, if I can get the pen over here somewhere, because I've made a couple of dumb mistakes already, make that 44.1. Goodness gracious. So the distance is 44.1 meters per second. You only have 2 significant digits. Count 2, 1, 2, look to the right. It's a 1 that's less than 5, so just round it to 44 meters. Now, how far is 44 meters? That's pretty close to half a football field down, okay? So that's pretty far. I wouldn't want to be falling in that well. That's a long way to try to climb up. And it's probably slick walls. If you watched Indiana Jones and he was able to do it, don't bank on not being able to do it, because y'all don't know who Indiana Jones is. Okay. Oh, here comes Diana. Okay, let me get her here. And I think we broke double digits. If I can find my roll book now. I don't know why I closed it. Oh, that's why I closed it. I don't have you in the roll book yet because I haven't gotten word that they finished with the schedules. That's why I had the people over here. Diana Patino is here. Okay. Now, since I was looking for roll sheets, I didn't notice. Is someone else trying to get in? Let's see what we got. Nope, we got 10 students. And let me make sure I've got 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. Got it. Okay. Diana, we're on page 38. It's chapter 2, motion. We're in section 2.4, which is, I think, called vertical motion. Yeah, falling objects. And we're doing example 1. Now they do have a second solution there that you could use. Okay, It just uses a different formula. And that's using the average velocity, and it just takes more steps to do that, and you got more formulas to remember. This has one formula, plug it in, you got it. So I don't think I'll do it, but if you want to take a look at solution 2, knock yourself out. Okay? Any questions on example 1? Angelita, are they seeming a little better? Not really? Okay, what we do is write down what we know, write down what we're looking for, and see if we can come up with a formula or formulas or steps that get us from one to the other. Okay, so let's see if I can get I can't get it to advance. There we go. So let's move on to compound motion, which is in 2.5. So far we've considered 2 types of motion: one-dimensional motion horizontally, and falling objects or vertical motion, objects thrown straight up in the air. Okay? Now let me give you, before we move to compound motion, let me give you a really dumb sounding example, but it's not just dumb sounding. It can be deadly. Now, I hope this doesn't happen in the US. Maybe it does. But I see in some third world countries, when some sort of big event is happening and the team very hotly contested, and the team that won whatever it was, the election or the concessions or whatever, and they get out in the street and they start firing their weapons into the air. Now, this is sort of gross, but if you were to fire that bullet straight up into the air, like throwing that pool ball into the air. Now when you fire a bullet, it has very little mass, but boy, it has a lot of velocity. If some of you are gun owners and know things about bullet speed, you may know how fast those bullets are traveling. So that bullet, if you fired it absolutely straight up, then every second it's going to decrease its velocity by 9.8 meters per second, because that's its acceleration downward, so it's losing that going upward. Well, if it's going at a phenomenally high rate of speed to begin with, and they usually do, then that just changes the speed a little bit. And then the next second changes it that same amount again, and again, and again, and again, and again. After so many seconds, finally the speed is slowing down until it reaches 0. At that point, it quits going up. Gravity now is still acting on it, and remember they said this thing? Acceleration is the same for all objects, whether they're going up or down. Trajectories exhibit up and down symmetries. So once that bullet's up there, that maximum height, way up there, then it starts falling back down. And if you fired it straight up, guess where it's heading when it comes straight down? And it's picking up speed every second at the same rate that it lost speed going up. So theoretically, when it comes right back to where you are, you're at muzzle velocity again. It's just like shooting yourself in the head. Don't do it. Don't fire a gun straight up in the air. Now when we get to compound motion, don't fire a gun anywhere up in the air unless you know there is nobody in its trajectory that it can hit. We'll get to it later. But it's, to me, a very important point. Okay? So let's get to compound motion. 3 types of motion. We had horizontal first, then vertical. Now we have a combination of horizontal and vertical, or vertical and horizontal. This is called projectile motion. This is what you're doing if you're on a ship and firing those weapons into the air to hit a target on land, or firing rockets. Now there's a little bit of difference between a gun and a rocket. As you give maximum speed to the gun immediately on leaving the barrel, and after that it's going to be slowing down, but not too awfully much. A rocket, on the other hand, if it's propelled, it can actually accelerate going. Okay? So it just depends on what you're dealing with. And then if you got a guided rocket, you still got other things to consider. So we're talking about firing the guns into the air. But the same thing goes for, oh goodness, what are they called? Those things that drop down the tube, light them, and fire up into the air. Grenades you usually throw, but there's something that anything like that that doesn't have its own means of accelerating, that's what we're talking about with compound motion. Because you do it at an angle. You don't want it to come back and hit you. We want it to go hit the other guy. Okay, the basic observation. Gravity acts at all times. Okay, the acceleration due to gravity, g, is absolutely independent on the object's motion. You fire it into the air at this angle, g's acting on it. That angle, g's acting on it. This angle, g's acting on it. This angle, g's acting on it. It doesn't matter. Whatever angle you fire the thing, acceleration due to gravity is acting on that object, independent on which direction it was when you first launched it. Okay? I'm losing my voice. I'm sorry. Let me see if a little bubbly soda is going to help that. I don't know if it helps it, but it feels good. Okay. Sorry about drinking in class, but here's kind of the bad news on my treatments. I mean, the treatment went great. I could tell it was being effective. I bet you if they took blood tomorrow when I go in, they're not going to, but if they did, you would see those white cells plummeted. The bad news is the red cells probably went down a little too. The hematocrits went down a little too. The hemoglobin went down a little too. And probably the platelets go down a little too. So this drug is a mean drug, okay? It's kind of like this coronavirus. If it can't find a white cell, it's going to attack something, okay? So coronavirus, if it doesn't land in your lungs, it's going to find somewhere else to go. So it's a monoclonal antibody, which they actually are testing some monoclonal antibodies on COVID to attack the places where it propagates. So anyway, sorry about that. I'm just explaining. I'm probably, even though the white counts are going to go down, probably the others will too, and I'll probably still be just as tired, if not tireder, next week than I am this week. But with the white counts down, hopefully then the red counts will start rebounding. That's our hope. And they want me to have another treatment in a month because my white counts were so high, and I said to them, can we do blood work before and have you make a decision on the blood work, not just, okay, let's just have it, because I've been over there on a Friday before and they'll say, oh, whoa, his whatever is low. I don't know. Should we give it? I don't know. Let's call the doctor. Can't get in touch with the doctor. Finally, someone will come in and say, well, let's go and give it to him. It's probably okay. I don't like that kind of attitude. I want them to do the blood work, say the Friday before the treatment. Then they evaluate the blood work and say, hey, let's wait another week, or let's wait another month, or something like that. Or, nope, your counts are rebounded. Let's go on and hit it again. Fine. So we'll see what happens. I'm kind of argue with the doctor sometimes. Okay, you're probably not supposed to, but I'm kind of stubborn that way. So for projectile motion with vertical projectiles, that's what I was just talking about, firing that bullet into the air. It slows on its way up, stops at the top, accelerates downward. The force of gravity acts downward throughout, slowing it down as it goes up, stopping it at the top, speeding it up when it comes down. The acceleration due to gravity, I hate they say the force due to gravity. The acceleration due to gravity acts downward throughout the motion of the object. Okay, horizontal projectiles, guess what? The horizontal velocity remains the same, because if you remember, a force acting perpendicular to the motion only changes direction. It does not change the speed. So the horizontal velocity remains the same throughout the problem. Okay? Well, you might say, well, then if I throw something horizontally, it's never going to hit the ground? No, 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 it didn't say that. The vertical component changes its direction, so it does make it hit the ground, but the horizontal component of that velocity is constant, but it's not constantly moving downward, somewhere going to crash into the earth. Okay, that's the stopping point. Okay, now if you put those two together, vertical motion slowing down as you go up, speeding up as you come down, horizontal velocity constant throughout, but vertical velocity picking up as it goes down, you get a curved path. Now, I'm just going to guess some of you probably have shot a basketball in your life. Yay or nay? Yeah, I thought so. Okay. Now, do you just aim for the rim of the basket? If you do, you're going to miss it every time. You throw up and it comes down. The only exception for that, the only one, and I've never done it, is dunking. I'm a white man, I can't jump. Okay. So dunking is just going downward, so you only have that one motion. That's vertical. But anything else, free throws, jump shots, anything else is going to go up and then down. That's a curved path. And what's the shape of that curve? It's actually called a parabola. Now this is a weird looking illustration and people don't believe it, but it's absolutely true. Here's this gal over here and this guy. The gal is an archer. So she's gotten her bow out, pulled the bow back, had the arrow in there, and is going to release it at the very instant the lazy guy down there is holding an arrow about the same height that she's firing from, and all he's going to do is drop the arrow. Which one hits the ground first? They hit it at the same time, because the only force acting to pull it toward the earth is the force due to gravity. That's acting on the moving one, it's acting on the stationary one. When she first fires it, it only has horizontal velocity. No, she's not firing it up or down, so there's no component of that velocity in the perpendicular direction, down. But gravity pulls it down, but the horizontal component is still the same as it was back here. Then a little bit later, because the acceleration due to gravity is increasing with time, so now the velocity is twice as much, say, as it was there. 3 times as much as it was there. Horizontal component never changes. What does this guy do? He drops it. He has no horizontal component. The acceleration due to gravity pulls it down that much, just like it did for her in the first second, that much in the second second, and that much in the third second. They hit the ground at the same time. Oh, hers had gone way further, for sure, but they hit the ground at the same time. Now that's assuming they're on a level field, and that's our assumption. That's what it shows here. Okay, so when you're target practicing and things like this, do you just aim straight for the target? No, you're going to go low every time. So what you do, some of your scales for your targets, if you've ever, I haven't ever seen the movies about snipers, but snipers are very good at estimating distances, and they adjust their scopes to move it up a little the further they are from it. They also adjust for wind velocity. They do all kinds of adjustments, and they know about what the velocity will do to the terminal velocity. So they got it all figured out. A good sniper does. They do lots of calculations, and this is what they do. They always aim high. Now, there's another sort of dumb illustration of this. If this gal, let's say this guy over here, has come over here and has climbed a tree, and somehow he got a watermelon up there. And at the very instant when she releases, he's going to release the watermelon, just dropping it, okay? Where should she aim then? Should she aim above the watermelon, at the watermelon, or below the watermelon? Because you know the watermelon's going to fall. Any idea? She really should aim straight for the watermelon, because as the watermelon falls, so does her arrow. So they should collide somewhere on down the way. If any of you have ever done any skeet shooting, I haven't, but I know some people in both mine and my wife's family have, and you want to fire just about the time the skeet gets its maximum displacement, and at that point that's where you fire right at it, and then the bullet hits it on its way down. You might have to lead it a little horizontally, but you want to be the vertical component just like that. Pretty amazing, but true. What you call that is leading it. You lead it horizontally, but aim right for it vertically. When it reaches that peak, that's when the vertex of that parabola, that's when you pull the trigger. I think. Physics in me says that. I've never done it. Now, passing a football. If that quarterback fires it straight toward the receiver, but the receiver's way down the field, guess what? He's going to underthrow him, because the ball is going to come down. So the quarterback, no matter how strong his arm is, has to have a little bit of a curve in it. It has to. No way around it. Okay? And here's the picture of that. This is on the top of page 41. Now, before we get to it, there is a science sketch on the bottom of the right-hand column of page 40. I think it's doing the same type thing that the picture up there is doing, so only if you want to do that again. So that quarterback, he's not going to throw, what do they call it, a clothesline pass. Now, if it's a very short pass, it looks like it's a clothesline pass, but look at that. He may be releasing it from over his head. The receiver is going to catch it about chest level. So even though it looks like he's throwing straight to him, it still is going down. And notice here, the horizontal component of it, he gives it an initial velocity. Once he gives it an initial velocity, then there's no more force acting on that at all. He pumps with his strong right arm, unfortunately here, and throws the ball, giving it a component of velocity just like this, tangent to that line right there. That has a horizontal component and it has a vertical component to begin with. Okay? The horizontal component never changes. They're always the same as the ball goes down the field. The vertical component is greater upward here, reduces because the acceleration due to gravity is pulling downward, actually goes to zero somewhere at that midpoint, now is heading downward, and hopefully the receiver is right there. And boy, Tua could lead that receiver perfectly. It seemed like most of the time they hardly ever broke stride. And good old Mac Jones seems like he's getting pretty close to that. I don't think he's quite as good at that. Every now and then they have to slow down a little bit or he overthrows them or something. But I guess Tua did too. But Tua was just amazing at being able to lead the people in stride and just go. Okay. So this is called the parabola. I think we talked about parabolas before. That's the motion. Now, you might say to yourself, isn't there some air resistance? Yes, there's always air resistance. But what are the best passes? How do they throw those? Anyone ever thrown a football? You try to get a nice tight spiral. You give it that spin action in it. Now, what that spin action does is kind of minimizes the air resistance. Well, guess what you have in a bullet coming out the barrel of a gun. I'm talking about a rifle now. Why is a rifle called a rifle and a shotgun called a shotgun? Aren't they doing the same thing? They're throwing something out into the air. Does anyone know why the rifle is called a rifle? Yes. Yeah, exactly. That's why they call it that. Rifling, it's not a good idea to look down the barrel of a gun, okay? Rifle, okay? But if you can open that and look down and there's absolutely nothing in it, you're looking in the direction the bullet would be going rather than the direction the bullet would be coming. You can see sometimes, especially if you hold a light there, you can see very, very tiny little etches, I guess you would say, which gives the bullet that spin. That makes it a truer shot. Now, I know we got 3 baseball players in the class. What are your positions? Can you tell me? Rucker? Yeah. What you? Oh, you don't? Oh, I'm sorry. How about? No, 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 no. That's right. You're GM students. I'm sorry. I was thinking you were baseball students. None of you are baseball students, are you? Okay. It's my trig class has 2. No. Yeah. And my algebra class has 1. So that's the class I was thinking of, not this one. Okay. Sorry about that. But if you've ever watched baseball, what does the pitcher just about always put on the ball? Some twist, some spin to it. Okay? Now, a fastball pitcher, that's mostly what he's interested in, just getting it there to the plate as soon as fast as possible, and he's got spin on it a lot like the spiral of a football, only a baseball is a spherical shape, not a oblong shape. Okay? Now, his pitches are going to be fairly true. Now, you can have a sinker fastball pitcher that right before it gets to the plate, it seems like it falls off the bottom. There have been some pretty good pitchers who had that pitch mastered. Easing up on the throw a little bit and either turning this way or that way, they have what, a curveball or a slider. I don't know which direction is which, but they're putting a horizontal spin on it, which makes the ball curve either away from the batter or to the batter. Okay? But you know the meanest, nastiest, deadly pitch to try to hit is probably the slowest of them all. Anyone know what it is? The knuckleball. The knuckleball, they try to throw it with absolutely no spin whatsoever. And in doing that, you don't have that advantage of your rifling out of your hand. You don't have that, so the ball moves more slowly, but with no spin, it's subject to the wind, the airflow that's going between you and the home plate. And if that changes or varies any, that ball could sort of jump all over the place. And the catchers who catch knuckleball pitchers have a glove that's about twice as big as the ones that catch fastball pitchers and curveball pitchers, because they know pretty much where those balls are going to end up. With a knuckleball, the pitcher doesn't know, the catcher doesn't know, and the batter doesn't know what that thing's going to do, and they are back there moving like crazy trying to get that ball. They don't want a pass ball. They don't want to cause a wild pitch because they went one way and the ball went the other way. So just some strange things about this. Sorry, way too much. Let's move on. I can't find the button. Okay. Now, no examples were given for compound motion. What was going to be the second lab, if we had been on campus, was a really nice lab the book came up with for doing that, but we'd have to roll balls down a lab bench and measure their horizontal velocities and then calculate what the vertical velocities and their speed and their horizontal displacement. It's really a pretty good lab. we're not on campus. So today we're going to be doing the laws based on the lab based on forces. And we talked about forces, and I said this book was sort of chopped up a little bit. Back on page 32, we talked about forces in a general sense. Now that we're talking about the three laws of motion, we're going to talk about forces in a more specific sense. Okay, so that's why I figured we could go on and do the force lab now, because I had found a two-dimensional lab, a virtual lab. It was going to be awfully hard to make up one that I did. Like the moving man we did last time, that was one-dimensional movement. I made it into one that you could do some calculations. The first time I taught it, which was last spring, when we had to leave campus suddenly, I didn't have any virtual labs done or anything. All they did was answer a few questions on it, and I gave them credit for it. This time I had more time to do it. The third lab before was a ladybug motion, and it does have some good things, but I couldn't think of how I could come up with 25 points worth of questions. I didn't do it last spring, just gave them credit if they turned it in. Okay, so we're doing the force lab this time, and we'll move on to that. The three laws of motion were first detailed by Newton. Notice they didn't say developed or invented or discovered by Newton. They were detailed by Newton. And one reason for that, the first law of motion that we're going to get to in a minute, was actually fairly nicely stated by good old Galileo, who came one generation ahead of Newton. Okay, and Newton read his work, detailed it, fixed it up, added a few words and caveats to it, and made it a bit more precise. And then he came up with the next two laws as well. Newton did. That wasn't Galileo. So they're usually attributed to Newton, though Newton used the first law of motion, came from Galileo's law of inertia, is what they call it. Okay? Now, Newton had to develop a brand new math to be able to explain these laws of motion. And that's when he developed the calculus, okay, which is a pretty hefty course, okay? And he also had to develop a law of gravitation, which we're going to get to toward the end of this chapter, okay? Maybe not today, but next time. The essential ideas in a lot of this was the idea of forces, okay? And you'll see the term force show up in all three laws of motion, okay? One place it's not there, one place it is, and one place there are two of them. Okay. So the first law of motion, like I just said, is sometimes called the law of inertia. Now, have y'all ever run into this term inertia before? Does it have any meaning to you? Well, what would happen if I wiped out these last two letters? What would that word be? Inert. What does inert mean? Not doing anything, not changing. That's why it's called the law of inertia. Okay? Now, one form of inert, we think of the couch potato. He just sits there watching his football or whatever he's watching, reruns, whatever he's watching, not doing a thing. That's inertia. Yeah, not moving. Okay? But inertia also comes into play when things are moving. So here's how Newton's first law, which he refined or detailed what Galileo had done. Every object retains its state of rest, like the couch potato, or its state of uniform straight line motion unless it's acted on by an unbalanced force. There's the force there. As long as there's no unbalanced force, that object, if it's at rest, it's going to sit there and stay there. Okay? If it's in motion, it's going to continue uniform straight line motion unless it's acted on by an unbalanced force. So let's give you a couple of examples of this. let's say that ball is on the golf key. Okay, I'm not a golfer, but I've watched too much golf. Any golf is too much for me to watch, it seems like. Sitting on the tee, I had to take golf at a program I went to one summer in high school. Not my favorite subject. But you put it on the tee, it sits there, and it sits there until you add an unbalanced force. You strike it with the club head. Of course, sometimes it sat there even after I tried to strike it because I missed it completely. So I don't really care for golf too much. But it's going to sit there unless it's acted on by an unbalanced force. But also, let's say that golf ball, once it's in the air, it's going to go in, it would go straight line motion unless it's acted by unbalanced force. Well, guess what? You hit that thing into the air, it's now under the influence of gravity. So that's not the law of inertia, okay? But let's go to the bowling ball rolling down the alley, okay? That's horizontal motion only. Horizontal motion does not change its magnitude because gravity is pulling downward. Well, it's a level floor. So that downward force does not affect the horizontal velocity. Horizontal velocity stays the same. So that ball retains its state of uniform straight line motion unless it's acted on by an unbalanced force. Okay? Now, for those who are good bowlers, I bet you know you can put spin on the bowling ball. They may call it English, okay, and get it so that it will have different air resistance on one side of the ball than the other. So maybe you can get it to curve in there and hit that very difficult spare, make it a spare rather than an open frame. I don't know enough about bowling, but we had to take that summer too. So, what is inertia? It's the resistance to any change of motion. If it's at rest, it wants to stay at rest. If it's in motion, it wants to stay in uniform, straight line motion. That's what inertia is. Now, we had, I think it was our previous lawnmower here, it may be this one, I can't remember. It started leaking gas in the gas line. There was a piece of plastic tubing that got a little slit in it. I don't know if something hit it or the gas ate into it. I don't know what, but it started leaking. At first it was just a few drops as I mowed and it wasn't bad. But then it got so I couldn't mow the yard on a tank of gas because it was leaking badly enough. So I decided to I had a pickup back then, to put the mower on the back of the pickup, and I found the place in town who did mower repair. So I was heading out there to get it. Well, I had chocked the wheels, or at least I thought I had chocked them pretty well. Well, somehow that lawnmower or the chocks or something moved, and every time I sped up, that lawnmower hit the tailgate. Every time I slowed down, the lawnmower hit the bed of the truck right behind the cab. And when I turned left, it hit the right-hand side of the vehicle. When I turned right, it hit the left-hand side of the bed of the truck. Why? Its inertia was trying to resist the change of motion. If it was going on at a certain speed and the truck slowed down, it tried to go that same speed and banged into the front of the cab, basically. Or if it's going on a certain speed and I hit the brakes, then it tries to go, I think I just said that. If I sped up the truck, accelerated the truck, then the lawnmower tried to stay at its rate of motion, so it fell behind, hit the tailgate. Turning, same thing. It's trying to resist its change of motion. I think we did the examples earlier of the person on the bus, hanging on. If he's not hanging on, that bus takes off, or the train at the Atlanta airport or something like that. If you're not holding on to something, it takes off in a hurry, you're going to fall back. Or when it comes to a sudden stop, you're going to fall forward. And the people around you will not be happy campers, okay? And also when it makes those bends underneath those, you better be hanging on or you're going to bump into the person next to you. Your inertia resists the change of motion. Oh, here's where we're going to have it. I'm sorry, I thought we had already done these. When the bus is initially at rest, you're at rest, okay? If the bus takes off, you try to stay at rest, meaning you want to stay in that same place, but of course the bus is moving out from under you, so you're falling backwards. Similarly, let's see if they have that one. No, it doesn't. If the bus was moving ahead and then came to a stop all of a sudden, you are moving forward then because you're trying to maintain that same inertia you had here, and the bus stops, you are still trying to move forward, okay? Or you're standing on the aisle of the bus, all the seats are taken, you're trying to be real macho about it and not hanging on to anything. If that bus makes a sudden turn to the right, wham, you bump into the person to your left because you're trying to maintain that same state of motion when the bus turns. And actually, it turns and hits you because you're trying to maintain your state of motion. Now, I can remember back when I was first studying physics, I don't know what grade it was, they didn't call it physics, they just called it science. We used to call that the centrifugal force. The force that throws you back when the bus takes off, throws you forward when the bus comes to a stop, throws you to the right when the bus turns left, throws you to the left when the bus turns right, throws you right when the bus turns left. They used to say that was the centrifugal force. No, it isn't, okay? There is no force. It's the bus cutting, changing speed under you. You're trying to maintain your state of motion. Actually, it relates more to a centripetal force as the bus pushes you into the curve. That's what the bus is doing there. It's not that you're being thrown in that way. The bus is pushing you to make you turn as well. Or the bus is dragging you along so you don't hit the back. Or the bus is stopping under you and trying to get you to stop too. Those are all, well, this one is a centripetal force, not centrifugal. Centrifugal force is basically an imaginary force. It doesn't actually exist. All right. Any questions on Newton's first law, the law of inertia? Okay. No problems or examples with the law of inertia. I bet you they'll come up with some in the back. Okay. Let me get a drink of water. My throat is awfully dry. I know I'm hoarse sounding. I think I may have mentioned to you before, they put me on a diuretic because all this, the white cells are going, basically being destroyed by this monoclonal antibody. So that's bursting the cells. They're leaving lots of junk in the bloodstream, and the whatever I just called it, diuretic helps flush them out of your system. So my goodness, I've just been going to the bathroom constantly, like 3 or 4 times a night. So I've taken the last 2 nights, and there the thing, of course, they were pumping me full of saline at the same time. I was just constantly going out. I was drinking stuff too, so I just get so dry because that diuretic is drying me out, and I think that's why my throat sounds like this. Okay, so now we move to Newton's second law of motion. Now let's go back and do a quick review. The first law of motion: every object retains its state of rest or its state of uniform straight line motion unless it's acted on by an unbalanced force. So basically, if it doesn't have one, it maintains whatever it was, either being at rest or moving in a straight line. Okay? Now, Newton's second law is kind of closely related to that. And it says if there is an unbalanced force that's done, then you have a change of motion. So forces cause, if you remember what acceleration was, a change in velocity. The change in velocity could be a change in speed like here, the bus was at rest, you're at rest, the bus takes off, that's a change in speed. The bus pulls you along, increasing you from the 0 speed to whatever the final speed is. Same thing if you're hanging on to the bus and it came to a stop, rather than being thrown forward, it is changing your motion. There are unbalanced forces then, and they change the motion, changing velocity. A velocity is an acceleration. But if you had this one, where the bus is pushing you this way, it's really not changing your speed that much, it's changing your direction. Here your velocity was in this direction, here your velocity in that direction. Constantly changing, and that's why Newton had to come up with the calculus, because no other math up to his time dealt with instantaneous change. And so that's what it's doing. It's pushing you down to change your direction, not necessarily change your speed. That is also a change of motion, because it's an acceleration. Any change of velocity, whether it's magnitude of velocity, increasing or decreasing, or direction of your velocity, any change is an acceleration. Forces, unbalanced forces, cause accelerations. Remember that one. Remember my example of the airplane at level flight, 500 miles per hour? We said there were no net forces. Lots of forces acting on it, but the net force, the unbalanced forces, was 0, because all the forces were balanced. Air resistance 500 miles per hour is not trivial. So that's why the engines are firing like crazy to keep that speed going, so you completely balance your velocity. Okay? And gravity is always pulling down on that plane, but the lift of the wings is lifting it up. And as long as you are going at the right speed to balance that out, then you have your lift. Okay? So there is no unbalanced forces. All the forces are balanced. The 2 horizontal forces are balanced, the 2 vertical forces are balanced. Okay? Now, the unit for force is a Newton. Okay? So basically what they're getting at here, if I can remember, oh, there's my pen. Okay. I couldn't see it. It blends in with the color of the computer. Okay. What it says here, basically another way you could express this, if I could get the pen to show up. Where are you, pen? There. No. Does anyone see where the pen is? There it is. Okay. This is saying force is proportional to acceleration. That's your good old directly proportional to. Forces cause acceleration. Okay? The unit for force is a Newton. We're going to get into that later. Unit for acceleration, we know that. That is always a distance divided by time squared. Okay? So this is going to be, let's just do it in SI units, meters per second squared. Okay? And this over here is a Newton. They haven't told us what a Newton is yet, but we'll get it in a minute. What is the proportionality constant? That you can change that proportionality to an equal K. Well, now it's not equal K, it's F is equal to ma, where m is the mass of the object. That's your proportionality constant. Okay? Now, what does that mean? If you have a system, okay, and we're dealing with systems here, a given mass, a given acceleration, and a given force. Increase the force, but leave everything out, leave the mass the same. Guess what? You're making it accelerate. Forces cause acceleration. A change of force creates a change of acceleration. Okay? So the more force, the more acceleration. However, if you have a bigger mass here with the same force, that means that your acceleration has to decline. So if you took a tennis, let's do a golf ball, and it hit it with a certain force, given force, hit it with a let's say a golf club, why not? Okay? And it's going to accelerate that golf ball, especially if you hit it nice and sweet and up, there it goes. Now, try doing that to a bowling ball. Take that puny little golf club that you used here and try to swing it just as hard, same force as you did to the golf ball, and you know what? I think the golf club's going to break. But even if it didn't break, the acceleration on that that bowling ball is going to be negligibly small. Because if you increase the mass with the same force, see, mass and acceleration are inversely proportional to each other. Okay? Inversely proportional. If that bowling ball were rolling down the alley and I took my foot and kicked it to the side, it's going to hurt my foot, but it would make it go into the gutter. Okay? If I were to do the same thing to say a volleyball or basketball rolling down the alley, wouldn't hurt my foot as much, but boy, the acceleration is going to be greater. Okay? A lesser mass with the same force is going to be a greater acceleration. A larger mass with the same force is going to be a lesser acceleration. More force, less acceleration. I'm sorry, more mass, less acceleration. Does that make sense? So here's your formula then. Now let's figure out what a Newton is. Okay? We know what we measure mass with, and this is why I chose SI units. Mass is measured in kilograms, in SI units. In the CGS system, it's measured in grams. The SI system is measured in kilograms. Acceleration, like I said here, was meters per second squared. So what is a force? A force has to be a kilogram meter per second squared. Units are your friends. Keep up with them. Don't let them help you do the problem right. Okay? And you see, mass, kilograms, where are you? Times acceleration, meters per second squared, that gives you force. This is what we call a Newton. A Newton is a kilogram meter per second squared. Get used to that. Just like I hope you're used to accelerations now. Accelerations are meters per second squared. Velocity is meters per second. I hope you picked that up from the first lab. Displacement or distance is meters. Okay, this is all SI units. Okay, so get to know these units, what they stand for, what they mean. Okay, I think that's what the next slide's going to do, so I'm going to erase my scribble here, and let's see what it does. Okay. All right, there it is. There's your net force is equal to your proportionality constant mass. Where is my cursor? There it is. Times the acceleration. That is one of the most famous equations and formulas in all of science. Force equal mass times acceleration. That's the Newton's second law equation. That says it all right there. Force is mass times acceleration. Okay? If a body is accelerating, meaning it's changed its velocity, there has to be a force. If there's a force, where is my cursor? I know it was here. There, I thought I saw it. This is bizarre. Where did the thing go? Maybe I have to click on this. There it is. If there's a net force, meaning an unbalanced force acting on it, it's going to accelerate. If the thing is accelerating, there's got to be a net force, an unbalanced force. Newton's first and second laws go hand in hand. This is Newton's first law said if there's no net force, the acceleration is constant. Okay? And meaning, okay, the velocity is constant, meaning there's zero acceleration. If the net force is zero acceleration, meaning the velocity is constant. Could be a constant zero, meaning it's not moving, or constant anything else, meaning it is moving. Okay. Now, I think there is where they talked about the units. They're not talking about them here, but I just did it on my last slide. So, here are some examples of Newton's second law. Okay? I think they leave some out here. But remember, more mass, less acceleration if there's a constant force. Okay? So we focus on the net force, and they're not showing the, okay, here's the guy riding his bicycle. Okay? Now, riding like that, he's exerting a force of the tire on the road, okay, which is pushing the bicycle forward, but there's always some friction of the tire with road, which is delaying that. Most of the time, that friction is not this great, okay? I don't think. Okay. Now, there's always some air resistance, especially if he's sitting up like this. If we go back to that picture of the racers, they are as horizontal as they can get. They're bent at the torso, so they present minimum, well, I called it in the Navy, we called it sail area. Okay, you don't want to have all that. All this wind hitting them here, especially if it's going fairly fast, that's air resistance. To me, the air resistance is way more than the road resistance. Okay, but whatever the relative sizes are, if these two are equal, then, and that in this, if these two added together equal the same magnitude of his applied force, does that mean he stops? No, that means he goes at a constant velocity. If the applied force is 0, then his velocity is constant. Now, if he's sitting there at rest, guess what? There's no friction with the road, there's no air resistance, no applied force, then the applied force is still 0, okay? This is wrong here. This word here should be net force. This is applied force down here. This should be net force here, okay? I'm sorry, I think I've taught this, I don't know how many times, the first time I've noticed that. This is net force, not applied force. There's the applied force here. If that's equal but opposite direction to the air resistance and the road friction, then you have a net force of 0, meaning he's going at a constant speed. Whether it's at 0 speed or 1 mile per hour, 2 miles per hour, 1 kilometer, whatever it is, 1 meter per second, whatever it is, he's going at a constant speed. Okay. Now we haven't gotten this part yet, but the net force here is 0. That's why I said this should be net force. Okay. The air resistance and tire friction match the applied force. Neither of those are 0. None of those, the way they've drawn them, are 0. It's only the net force is 0. No acceleration, but if this is an applied force and he has these resistance, he's going, but he's going at a constant velocity. So the acceleration, which is change of velocity over change of time, is 0. So there's no acceleration, no net force, no applied force. Okay. Sorry they messed that one up. Did they get it right in the book? Yes, in the book they did say, figure 220, they said the net force is 0, not the applied force. Okay. Whoa. Now, hold on. I'm going to skip a few slides. See, that's the one they should have done with the football, but they didn't. We'll do something there. Nope. I swore they used to have that other picture in the slide set, and they don't anymore. Okay? Okay. I'm going to show it to you in the book. If you got your books, you've already seen it. Okay, now the same guy is on a bicycle built for 2, but he's the only one on there, and he's going along pedaling, and let's say he's going at a constant speed, meaning that his applied force is equal to the sum of the road resistance and air resistance, but in the opposite direction. Now his girlfriend, wife, some gal gets on board, and boy, isn't she the lazy one. Notice her pedals are not on, her feet are not on the pedals. She's letting him do all the work. Okay, now let's just say that she was the same mass as he was. What have you done now? You've doubled the mass. You decrease your acceleration. Okay, he's either going to have to do twice the force, applied force, to maintain that net force of 0, or if up there he was going at a net force, say, of 1 meter Newton in the to the right, if she gets on and doesn't do anything, now he's only going to be doing it 2 newtons to the right, if that's his net force. Because the mass doubled, we're saying she weighed the same as him, but she wasn't applying any net force. So she's making him do all the work. Story of my life. No, I didn't say that. All right, so before we move to weight and mass, example 2A. How long have we been going here? We started 3:15, 4:47. That's an hour and a half, basically. Let's try to get at least 2.5, something like that. Let me drink some more Coke. I'm just running out of energy. Okay, I'm not sure that's doing any good, but it's a good placebo anyway. So let's go to the whiteboard. All right, I've got a little bit of housekeeping to do here. They have this taskbar in the white space, where I'm going to move it out of the white space, frees me up more white space to work on. Your names are over here on the right-hand column. You can't see, but they're there taking up rectangles. So I want to move the white space as far to the left as I can to get them as far away from your names as possible. I can't get them completely. It's still covering part of it, but so it covers the minimal amount. So that gives me the most white working space. All right, here's example 2, just for Angelita, because she loves these examples. Okay. A 60 kilogram bicycle and rider, so it's a bicycle and rider, accelerates at 5.5 meters per second squared. So the 60, and they don't put a 0.0, kilogram, and it's the bike and rider. I'm just going to do B and R, okay? Now what's that a measure of? 60 kilograms. What unit, what quantity does a kilogram measure? Okay, 1,000 what? Grams, okay? But what does that measure? What physical unit are we measuring there? Mass. 60 kilograms, that is the SI mass unit, okay? So that's measuring mass. And we just told he has an acceleration of, I don't know why it won't draw an equal sign the first time, 0.5, and look at those units, meters per second squared. Yep, that's a good unit for acceleration. Make sure they make sense here. Now that seems pretty small, but guess what, folks? That's not a bad acceleration. That means he's increasing his speed 0.5 meter per second every second. And guess it, if he's going very many seconds, he's going to be going awfully fast in a fairly short time. Now, I don't know if our AC kicks in around 5 or something like that, but I'm getting a little chilled. And let me, oh, yeah. I hope I turned it off. Doesn't look like it. That looks like it may. Or not. Nope. That's 4, 3, 2, 1. I hope that's it. Nope. 1, 2, 3, 4. I hope that turned it off. I'm going to wear out the fan just trying to manipulate it. Just shows my body, mind is just not working together too well. I think it's stopping now. Okay. How much extra force was applied from when the bike was flying at a constant rate? Okay. Well, what's the Newton's second law equation? Net force is equal to what? Mass times acceleration. Now remember, even when he was going at a constant speed, zero acceleration, he was still having to do a applied force. He had to pedal some because he was hitting air resistance and he was hitting road resistance. So he has to be applying some. So what it's saying here, how much more force, that's what it means, extra force was applied to make it accelerate at that amount. So that's the net force we're talking about here, beyond what he was doing before, or she, whoever it was. Well, that's 60 kilograms times 0.5, that's not drawing well, meters per second squared. If I slow down, it does a little better. That would be 30 kilogram meters per second squared. And does anyone remember what a kilogram meter per second squared is? Newton. That's what a kilogram meter per second squared. That's what we measure force in the SI units, is Newton. Named after good old Sir Isaac. Now, is someone talking to me, or is your microphone just on? Oh, okay. You got it then? Good, excellent. All right. Then at the bottom of that page, it says, it's a different problem. Can we do the same one here? Let's see if we can. Okay, I'm going to draw a line to separate these two. And at the bottom page it says, what is the acceleration? So in this case, acceleration is the unknown. Now, I didn't put that down. Before, the net force was the unknown. And we found the unknown by that formula, plugged it in. Here the acceleration is the unknown quantity. What is the acceleration of a 20 kilogram cart? 20 kilogram would be measuring what? What does kilogram measure? Mass. Excellent. Okay. And if the net force on it, so here's the net force, F sub n is equal to 40 newtons. And what is a newton? What is it? Basic units? Kilogram meter per second squared. That's what we did right here. Kilogram meter per second squared is a newton. Okay, remember that. Okay, so what's the formula that relates acceleration, mass, and net force? You better get that one. It's right up there. Net force equal mass times acceleration. I often call that the second law formula. Okay, now since we're looking for acceleration, let's divide both sides by mass. You can go to your circles or triangles if you wanted to. They disappear. So this would be net force of 40 newtons. No, I want to write the basic units. That's why I wrote them down there. Kilogram meter per second squared. That's a really ugly K, isn't it? Okay, kilogram meter, still pretty ugly. It's getting worse. Okay, let's see if I can improve on that just a little bit. I can't get my pen. There it comes. Okay, let's get all of that mess out of there. Okay, that's a kilogram meter per second squared divided by the mass, which is 20 kilograms, And guess what? The kilograms cancel out. 20 will go into 40 exactly 2 times. So you have an acceleration is equal to 2. What units do you have left? Meters per second squared. Excellent units for acceleration. That's what you measure it in. Now, just a little hint. You're not going to be able to maintain that very long because it's increasing speed at 2 meters per second every second. So after the first second, you'll be at 2 meters per second, maybe. The next second, you'll be at 4 meters per second. Next second, 6 meters per second. After a while, you're going faster than you can probably think of going. And what was that, a bicyclist? Or no, a cart. Yeah, you're not going to be running carts at really high rates of speed. So this is only going to be good for a few seconds. Okay, let's see if we got the answer they did. Yep, 2 meters per second squared. Good for them. Now, they do show a second law experiment, and I have done one like this in lab before, especially when I was doing demonstrations back before we had labs, when we were at Western State Technical College and we didn't have labs, trying to do this. But you always have friction, and if there's any differences in your surface, it could change at time. It was a pretty tough lab to do, but you could do it if you got a nice smooth surface, a nice rubber band, that kind of stuff. You can do that. All right, now let's talk about weight and mass. That's the next topic here. Let's go back to our, and by the way, we still have 10 students here. Let me see if that, no, 9 students here. We dropped one, I think. 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I had 10 at one time. We've dropped to 9. So sorry about that. Maybe that was one of the beeps I heard earlier. Okay, chapter 2. Let's go back to chapter 2. And let's go resume the slideshow where we left off. There was a guy on his bicycle. Now we're talking about weight and mass. This is at the beginning of page 44. Now, in everyday usage, unfortunately, we almost use these terms as if they're equivalent. They're not. They differ only by a constant most of the time, so therefore we can treat them as if they're equivalent, but they're not. Number one, weight is a force. Its units are, if it's in newtons, kilogram meter per second squared. If it's in the U.S. customary, it's in pounds. That's what we measure weight by. Forces are vectors. Weight has a direction, always toward the center of the earth. Okay? Mass, on the other hand, is a scalar quantity. It's measured in kilograms. In the U.S. customary system, there is a unit for mass, and nobody, I want to say, ever uses it. Some physics books will use it as if you use it all the time. No one in real life uses it. Does anyone even know what the unit of mass is in the U.S. customary system? Probably not. It's a slug. S-L-U-G. It's not used. No one even has an abbreviation for it. If you ever used it, you have to spell it out. Okay? It just as you never go in the grocery store and say, I want to buy 5 slugs of potatoes. They would look at you. Our potatoes don't have slugs. You know, no one would know what you're talking about. Okay? You go in and say, I want 5 pounds of potatoes. But if you're being very metric about it, you go and say, I'd like 5 kilograms of potatoes. Why? Look at the scales. And the scales in the grocery store will have pounds on the outside and kilograms on the inside. And the arrow points to some number in kilograms or some number in pounds as if they're equal. They're not equal, they're equivalent. Okay? Most of the time they're sold per pound, but if you're in Canada, Europe, just about anywhere else in the world, except for a few of the countries that deal mostly with U.S., everybody uses kilograms, mass, not weight units. You could buy so many newtons of potatoes, but They don't do it. They use the mass of potatoes. Okay. So the mass is a quantitative measure, meaning it only has a magnitude of inertia. It's a measure of your inertia. Remember that bowling ball and the basketball rolling down the bowling alley? That bowling ball had a lot more inertia. It was harder to change its direction because it had more mass. Okay? The amount of matter there is, a scalar quantity with no direction associated with it, that's mass. The SI unit for mass is kilogram. The CGS unit is gram. U.S. customary hardly ever uses it. If you ever did, it would, well, actually, it would be a slug if you use it properly. Back when I was growing up, they would throw in something they called a pound mass. You're actually measuring in mass pounds, but then acting as if that was measuring mass, which was a weird, strange. It's just strange. Okay. What is weight? Weight is a force, not a quantitative measure, a vector measure of gravity acting on the mass. So remember that earlier slide. Let me see if I can go back to it real quickly. Yep, I missed it. But remember I said, it said the force due to gravity. And I cannot see it now. And I said that should be acceleration due to gravity. I don't know if you remember that. I can't find it now. I know it was back there somewhere. But if you're talking about the force due to gravity, that's weight. That's not acceleration. G is not the force due to gravity, it's the acceleration due to gravity. Weight is the force due to gravity. That's your mass times your acceleration due to gravity, mg. We'll get to that in just a minute. In fact, it's right there on the slide. So pounds and newtons measure force. Pounds in U.S. customary, newtons in the SI units. Okay? Whereas kilogram measures mass in the SI unit, and we don't really have a working definition for a unit in the U.S. customary. We have one, it's a slug, but no one uses it. So they don't even mention it here. So what they're doing here is showing the equivalence or the relationship, how they compare. This is Newton's second law of force, second law formula. Net force equal mass times acceleration. A mass in kilograms times an acceleration in meters per second square gives you a net force in newtons. We've just been using that. Okay? However, when we're talking about the force due to gravity, then weight is that force, and that's your mass, and then it's multiplied by the acceleration due to gravity, which is this, 9.8 meters per second squared. Now, I'm a little surprised at this book. A lot of physics books always list that as a minus 9.8 meters per second squared because they always count going straight downward as a negative direction. This book treats it as if that's your positive direction going down, so anything going up would be at a negative, which is a little bizarre, but it's okay. Now, what this is meaning, if the only force acting on an object was its weight, then the net force is the weight. The mass is the mass, and the acceleration, the only acceleration, is the acceleration due to gravity, which is 9.8 meters per second squared. So they wrote this as if it's always the case. That would be if that's the only force, the net force acting on a body, then this is equivalent. Quite often in our problems, you have a net force, and then you have one of the forces acting on it. Remember the airplane flying at constant speed. Gravity was huge going downward, mg, but the net force was zero because it was going at a constant speed and all the forces were balanced. That force due to gravity exactly balanced by the lift caused by the wings and your velocity. Okay. Make sense, sort of? the main thing they're showing there is how similar the forms are. And yeah, hang on to them, because force in newtons equal mass in kilograms times acceleration in meters per second squared, where you're talking about a net force, an applied force, any kind of force. This one would be weight, mass times the acceleration. In this one case, it's always the acceleration due to gravity. And everywhere on the surface of the earth, if you're at the bottom of the Dead Sea Valley or on the top of Mount Himalaya, this changes very, very, very little. Okay? However, if you're up in space, it drops off big time. Okay? And most of the time we don't use it underground. So don't sweat that. So that was Newton's, that was your weight and mass. They did do 2 examples with that one. So let's get our whiteboard back and do our 2 examples. Oh man. Yeah. Let me get another sip of something here. In addition to everything else, I was trying to get everything ready for today's class. So I was up till after 10 last night, but because my appointment this morning was at 7, I had to be, I think I finally got up about 5:30. So it's been a long day already. It was an 8-hour day at 3 o'clock. That was before the class started. Okay. In fact, at 2:30, it was an 8-hour day. Not of work, but of being awake. Okay. Now, the table 2.1 that's in your book, I'm going to show it to you. If you got your books open, you probably already noticed it. This gives some of those units. Okay. So let me, I can't read them backwards, too small and that kind of stuff. In the metric system, I don't like them saying that, oh, here's someone coming in, Valerie. Oh, she must have had to bump out and come back. She said she was at work, so I already have her present. She must have had to shut out and then come back in. So let me make sure I do have her here. Yes. All right. So when it says metric system, it should say SI system. There are a little bit of difference between metric system and SI system. SI system. The mass is kilogram. The acceleration is meters per second squared. Your force is kilogram meter per second squared, which is a Newton. Okay. Now, in the English system, this is the one I was talking about. They call that a pound mass. That's a pound per foot-pounds per second squared. Really strange, convoluted gyrations of units. And then multiply that by feet per second squared, and you get pounds. That unit they listed there is what they call a pound mass. Okay? The actual U.S. customary unit is slug. And slug, they also measure by feet per second squared and get pounds. So a pound mass and a slug are actually equivalent things. But see, a pound mass, you have to do lb mass, sub-mass. So that's actually longer to write than slug. But at least people kind of know what you're talking about then. But anyway, let's move on and do example 210. So I'm going to clear the, does anyone need me to leave these 2 up there a little bit longer? Everybody got it? Valerie, did you get it coming back? Get it on the YouTube video? Okay. And it's in the book too. Okay. Thanks. All right, so we'll clear that. And let's do example 210, bottom of page 44. What is the weight? And remember, the symbol for weight is little w. I wish I had my PowerPoint back up. I'd show it to you. I cannot see my pen. It's done this several times today. In this class, the cursor just disappears. And it's on the draw mode. Oh, duh, that's my fault. I was doing it on the pad, not on the Wacom pad. Okay, there it is. So where was it? What is the weight? The symbol for weight is little w. That's your unknown in this problem. What is the weight of a 60 kilogram person? So 60.0 kilogram is your numerical value. What is that measuring? Mass. Kilogram measures mass in the SI units. What is the weight of a 60 kilogram person? 60.0 kilogram, 3 significant digits here, and the acceleration due to gravity, so we're also looking for A. Well, wait a minute. Oh, no, I'm sorry. They're giving us A. And the acceleration due to gravity, G, which we're going to call now G, is equal to 9.8 meters per second squared. Now, they do this to you sometimes, and I find it kind of obnoxious. Okay? This one, they gave you the acceleration due to gravity as 9.8 meters per second squared, and sometimes they'll give it to you as 9.80 meters per second squared. Well, the difference, this is only 2 significant digits. Despite the fact that's 3, your weight you can only give to 2 digits because you can't get any more precision out of the problem than you put into it. You only put 2 digits there. And it says on the surface of the earth, so that's why we can use G. Okay? All right, well, what is weight? That formula looks a lot like Newton's second law, whereas Newton's second law is net force is mass times acceleration. Here your weight is your mass times the acceleration due to gravity. Pulling you down, that's your weight. Okay? So this, we just plug and chug. Mass, 60.0 kilograms times acceleration, 9.8 meters per second squared. Have to write slowly or the pen screws up. So 6 times 8 is 48. I think we'll lose a decimal. We'll lose a decimal place there. 6 times 9 is 54, and 4 is 588. And that would be kilogram meter per second squared. But what is a kilogram meter per second squared? That is a Newton. But here's where they mess with your mind here, because this only has 2 digits. You count 1, 2, look to the right, that's greater than 5, so bump that up by 1 and call it 59. And what's a kilogram meter per second squared? Newton. I hate it if my scale did that to me and I was I left off my 0. I was really 588 newtons, and it told me I was 590. I want that 2 newtons taken off of there. But no, we only have significant digits, and that's why they give you the answer as 590 newtons, 590 newtons, where that 0 is not significant, only the first 2 digits are significant, okay, because that's all you had coming in. So let's see if we can get example 211 on the same page. Where I see the pen, but it's not moving when I'm moving. Come on. There, it moved. Okay. All right, so let's do 211. A 60 kilogram person, what's that a measure of? That is the person's mass. Now, frankly, pretty massive person there. A rule of thumb is multiply it by 2.2 and you get about how many pounds it is. Okay, that's just a rule of thumb. That would be 12 plus 120, that would be 150. Yeah, 152 pounds. So that's not all that big. Okay, I was thinking it was bigger than that. Okay, but this person weighs 100 newtons. Come on, pen, move. There we go. 100.0 newtons. And I won't put what units newtons are. Can someone tell me? Kilogram meter per second squared. Mass times acceleration. Okay? On the moon. So this is his weight on the moon. That little m stands for moon. That's a little w too. It may not look like it. What is the acceleration due to gravity on the moon? Like I said, most of our lives, mine, I'm always going to be on the surface of the earth, or as close to it as I can possibly be, okay? But this is an astronaut that went to the moon. So what is the acceleration due to gravity there? We're looking for acceleration, so our formula, basic formula, is the one up here. Weight is equal to mass times acceleration due to gravity. Most of the time we use Earth here. Now we're on the moon, so we're going to use the moon's gravity, and that's what we're looking for. The mass doesn't change. How much of that person there is the same here on Earth as it is on the moon, as it is out in deep space, as it would be on Jupiter or Venus or Mars or Saturn or wherever you would be. The mass doesn't change. The weight changes big time. So this is the weight on the moon. So I'm going to put W sub m there. Well, that's what we have here. Well, we're looking for, what is the acceleration on the moon, of gravity on the moon? Not the same as on Earth, guarantee it. So, like I said, that would be well, we won't go into that. Okay, so let's solve for Gm. So what we're going to do is divide both sides of the equation by mass, and the masses go out here, giving us our acceleration due to gravity on the moon, which is exactly what we're looking for, and that's going to be his weight, which is 100.0. I don't know why they gave us 4 significant digits there. I like to use the full digits: kilogram, fundamental units, meters per second squared. Divide that by the mass in kilograms, 60.0 kilograms. Notice the units of kilograms go out, and if you pull out your calculator, basically this is, all these go away, and that's 5/3, so that would be 1 2/3, 1.67. Now the reason we only do 3 digits, this is only 3 digits there. Even though that's 4, we can't get more precision out than we put in. So it was 1.666666. Count off 3 digits, look to the right, 6 greater than 5, bump that up to 1.7, and this would be meters per second squared. Now, if you, I doubt if you were alive to see them, because the Apollo moonwalks and all that kind of stuff happened back when I was in high school and college type age. You probably weren't even born yet, but if you've ever seen the videos of that, you would have noticed that those guys kind of bop along, like rabbits, even though they got this really big heavy equipment on. They look very light, and the reason is their weight is very, very small. The mass is the same, the weight is small because the acceleration due to gravity on the moon is about 1/6 that what it is on the Earth, approximately. Okay, how did they do? 1.67 meters per second square. Good for them. Okay. Now, we've just passed the 2-hour mark. Let's see if we can make it to lab. Basically, I'm meaning I can make it to lab. I think I can. Like the little train said. Okay. Okay, we'll resume the slideshow if I can get this to pick up here. Again, my cursor sort of disappears. So there was weight and mass. Now we go to Newton's third law of motion. Okay? Now, remember how closely connected the first two laws were. First law said that an object tends to maintain its state of inertia. In other words, if it was at rest, it tends to stay at rest. If it's moving in a straight line fashion, it tends to keep the same direction, same speed, not changing. If there's no net force acting, an unbalanced force acting on it. That was the first law. Galileo's law of inertia, Newton refined it a little bit. Then Newton took it a step further and said, but if there is a net force acting on it, then there's an acceleration. What is acceleration? Change of velocity. It could be speeding up, it could be slowing down, it could be changing direction, or anywhere in between. Now, both of those laws dealt with an object, and you're doing things to it, exerting a net force on it, giving it velocity, giving it acceleration, whatever. You're dealing with an object, the bowling ball, the basketball, the tennis ball, whatever, okay? That is a rock. Whatever it is, you're dealing with that object. The third law talks about the relationships between different objects, okay? Let's go back to the kicking the bowling ball. Not a good idea, remember? It's rolling down the lane. You're standing while you're there. They're going to get all over you. You go and try to kick the ball while it's rolling down there. It's going to hurt your foot big time because you have now done a force on the bowling ball. But guess what? That bowling ball also did a force on your toe. That's the third law. It relates the forces between two objects. And here's how it usually reads. Whenever two objects interact, the force exerted on one object is equal in size but opposite in direction to the force exerted on the other object. Couple things to remember here. Forces are vector quantities. They have magnitude, they have direction. When two forces interact, two objects interact, the force exerted on one object is equal in size. That means the magnitudes are the same but opposite in directions, okay, to the force exerted by the other object. Now, I've heard it said, read somewhere, that Newton explained it this way. And I can't show you anything, I don't think. Let me get something sort of pointed here. This may work. Here's a pen I brought in from campus. Okay, if I exert a force on the end of the pen, push on the end of the pen, I'm pushing on the pen. But guess what? The pen's pushing on me. Where is my camera? You see the indentation? It pushed back on me with an equal opposite force. Hopefully that will go away in time. Okay, that hurts. Okay, that's exactly what's happening. Kick a rock. The force with which you kick the rock resists its motion and pushes back on your foot in the same magnitude, opposite direction. Okay, that's Newton's third law. It deals with two objects, and you deal with two forces that are equal in size, opposite in direction. Okay, that's all the slide they had on Newton's third law. Okay, let me see if they gave some examples. They actually did do something that I think is worthwhile for me to write, so I think I will write it. It's actually one of their equations going to list at the end, and where is the best place to write it? Maybe right down here. Let me try here. Here's what it means. F sub A due to B, and this is why they don't usually write it, the subscript's longer than the formula, is equal to, and this I don't like, these are magnitudes. If you're doing it properly, minus F sub B due to A. Now basically that's saying the same thing we did. The force on A from B due to B is equal in magnitude. That's what their equation was showing, but opposite in direction. That's why I put the minus sign there. So I'm going to go on and put the vectors here. This is a vector equation now. It's supposed to be an arrow there. Okay, get out of there. This is so aggravating. You draw something and then it changes it. Okay. Equal but opposite in direction to the force on B by A. And sometimes they'll do A, B, B, A. And as long as you understand which one's representing what, that's it. But I did feel like they should at least give you that. They do have two examples. Okay. Let's see if we can get these done. So this will go to the slides, the whiteboard. I don't know why that didn't work, but it did. Okay, there we go. Does anyone need this one any longer? These two examples. So here's example 2-12. A 60 kilogram astronaut. Hang on to this concept for a bit, folks. You're going to use it over and over again. 60.0 kilogram astronaut. So I'm going to, okay. What is that a measure of? Mass of the astronaut. Is freely floating in space, and he happens to come up to a freely floating 120 kilogram spacecraft. Now, that freely floating, that means the astronaut's initial velocity, I'm going to call it A sub I, astronaut's initial velocity is 0 meters per second. Okay, that's a good unit for a velocity. We're in metric units of meters per second. You could put 0.0000, doesn't matter how many, as many significant digits as you want. He's not moving. Okay. I think I'm going to go and put my vector symbol there too. I should have been doing that all along. The book didn't, and I failed to. Now he runs into a spacecraft. I don't know how. Maybe I don't know. Maybe he was standing next to it, floating next to it. Oh, anyway. And there's a 120 kilogram spacecraft. Well, that's the mass of the spacecraft. Okay, that's 120, and I think they put 0.0 for some reason. Kilogram spacecraft. That is a mass unit. And it's also freely floating, so its initial velocity of the spacecraft is also 0 meters per second. Okay, as many decimal places as you want to. Okay? Now he pushes on the spacecraft. So this, I'm going to put the force of the spacecraft by the astronaut. Okay? I'll put that as vector quantity. Okay? Is 30.0 newtons. Okay? Now again, I like to put that in fundamental units. Kilogram meter per second squared. Okay. For 1.5 seconds. So here we have a time interval. Delta T is equal to 1.50 seconds. Now, for us right now, that's probably extraneous information, because none of our formula, well, no, I don't want to say that. We may use it, okay? Hang on to that. 1.50 seconds. Okay. Now, that's all the given. Here's the A part. If I could get my pen. There you went. Okay, the A part here. compare the forces exerted on the astronaut and the spacecraft. If the astronaut pushes on the spacecraft, compare the forces, that force that we were just told about, that force of 30 newtons, with the spacecraft on the astronaut. Okay, so we know that the force exerted by the astronaut on the spacecraft is 30.0 newtons. I'll leave newtons there for now. Okay, now compare that force with the exerted by the spacecraft on the astronaut. So we want to do force of on the astronaut by the spacecraft. Okay, now that's going to be the mass of the I think we're going to have to do something here too. This will be the mass of the astronaut times the acceleration of the astronaut. Okay, I think that's what they're asking for, isn't it? I forgot to write it down. Compare the forces exerted. No, this was the unknown. I should have put my question mark there first. Okay, mass of the astronaut times the acceleration on the astronaut. Okay, acceleration, by the way, is a vector quantity too. But frankly, it doesn't matter, because what does Newton's third law say? This has to be minus that. Remember, the force of one on the other is equal but opposite in direction. So that's a minus 30.0 newtons. Okay, that's all the first part was looking for. The force of the spacecraft on the astronaut is equal to the force of the astronaut on the spacecraft. Got to be equal in magnitude, opposite in direction. That's what the minus sign stands for. The 30s are the same. Okay, so that's done. In the book, they said the magnitudes are equal. Okay, if they wanted magnitude, they should have said magnitude, but it says compare the forces, I think, but it does say at the bottom, but in opposite directions. Okay, now we still haven't used the delta T. Okay, so don't get bent out of shape. The second part of the question here, the B part, says compare the acceleration on the astronaut to the acceleration on the spacecraft. Okay, so since this is a spacecraft, we'll do force of astronaut on spacecraft is equal to mass of the spacecraft times acceleration of the spacecraft. We know the force, they gave it to us. We know the mass, they gave it to us. I couldn't find it. There it is. Okay, did I write it down? Yeah, there it is. Okay, so we're looking for acceleration. So this implies that the acceleration of the spacecraft is equal to the force on the spacecraft by the astronaut divided by the mass of the spacecraft. Okay, yeah, that means implies. Okay, so this is Newton's second law here. Force equal mass times acceleration. This is force on the spacecraft by the astronaut. That's what the second one stands for. This is the mass of the spacecraft, acceleration of the spacecraft. We're looking for the acceleration of the spacecraft. That's the unknown here. I didn't write that down. Acceleration of the spacecraft in the B part. I should have written it down here. That's the unknown. Acceleration of the spacecraft, that's what we're looking for. And then we're going to do the acceleration on the astronaut, and we're going to look for that as well and compare the two. Okay, that's what we're doing. So this one, we're finding out what's the acceleration of the spacecraft. I'll go on and put my arrow over it again here and here too. That indicates the vector. Okay, so this acceleration on the spacecraft is the force on the spacecraft. We just found out they gave it to us as 30.0, and now I'm going to use my full-fledged units, kilogram meter per second squared. When I do my calculations, I usually like to use fundamental units. Okay, divided by the mass of the spacecraft, which they give here to be 120 meters. They put a 0.0 there. They don't need it, but I put it there. Here the meters go out. So the acceleration on the spacecraft is equal to 0.25. Divide 30 by 120, or divide 3 by 12, that reduces 1 over 4, and that's 0.25 meters per second squared. Those are the units. No, I've crossed out the wrong units. How did I do that? 120 kilograms. That cancels that, not that one. Sorry about that. I'm getting too anxious for my break here, I think. Where I have to... here are the erasers up here. Now the eraser won't activate. I don't know why it does this. Somewhere in the class, in most classes, at some point, it just quits working. I can't get it to work. So the kilograms cancel out, not the meter. I was thinking mass. So that gives you meter per second squared. 2 significant digits cause that. Well, wait, you need a third one, don't you? 0.250 meters per second squared. Because that is 3 significant digits, that's 3 significant digits. And that's a positive, in the positive direction. We're also going to compare the acceleration of the astronaut. And it's got the same type formula, too many A's there. That's the net force on the astronaut by the spacecraft divided by the mass of the astronaut. Just like that turned out with S's there, these are going to be your A's. Okay? And that we knew was minus 30. That's why I put a vector quantity, 0.0 kilogram meter per second squared divided by the mass of the astronaut. He was, or she was, or it was 60. And by the way, masses are always positive. Can't have a negative mass. There's some body there is going to have a positive mass. The kilograms cancel out, and that gave you, if you get your calculator, that gives you 3 over 6. So it's minus 0.500 meters per second squared. Okay. Now, oh my goodness, how are we doing on time? Got 5 minutes. Let's see if we can get this done. Okay, so what do we see? The acceleration of the spacecraft is half the acceleration of the astronaut. Remember, this is, come on, where are you? There you are. Acceleration of the astronaut. It's half as much. Why? Because the spacecraft was twice as massive. If you increase the mass, you decrease the acceleration. Inverse relationship. Okay? And for some reason my equal signs, oh no, that's my negative sign. Okay. So we've done the A and B part. I've lost it here. No, that just asked for the two things, and what we got was the first part says both were 30 newtons of force on them. That was the first part. but they were in opposite directions, so that's why I put the vector quantities and put the minus sign. Okay, doesn't matter which one you listed, positive and negative. Okay, for the spacecraft, then the acceleration on the astronaut they did first was 0.5 meters per 0.00 meters per second square. For the spacecraft was 0.25. But again, they should have opposite directions. They're just dealing with magnitudes. I included the vector quantity. Okay, we still haven't used the delta t, and that's what example 213 is going to do. After the interaction and acceleration between the astronaut and spacecraft described in example 212, they both move away from their original positions. What is the new speed for each? Okay, so I'm going to try to get it down here. If I can't, I'll erase some stuff up there. Okay, so we're looking for V final for the astronaut and V final for the spacecraft. These are the unknowns here. Okay, and we do know, if you recall, I just don't have room to write it, so I'm going to start erasing. I don't know where to erase though. Let me write it up here. Let me think of the best way to do it. V final is equal to, go back in earlier in the section here, V initial plus AT. Yuck. I'm writing near the top and I can't get the thing to disappear. It'll fade out in a minute and probably take away part of what I did. Yep, it took out the plus sign. Now V initial plus AT. That's the formula we'll be using. We'll do it for the acceleration for the spacecraft. We'll do it for the astronaut. That's where our delta t comes into play, and I'm losing my voice like crazy. So this is going to be V initial for both of them is 0. So we won't even write that term down. Save some space. And we have acceleration of the astronaut was a minus 0.500 meters per second squared times your time interval 1.50 seconds. And that was a really ugly one. Okay, so 5 times 1.5 is 75, I think. So that would be minus 75 0. I'm sorry, I forgot my unit. 0.75. I wish I could get my eraser back, but I can't. 750, in fact, meters per second. Because you see, this second here cancels one of those seconds out here, giving you meters per second. Let's do the same thing for the spacecraft. It had the same acceleration, but no, it didn't. It had half the acceleration. 250. Keep making errors. 250 meters per second squared times the same 1.50 seconds, and that second cancels one of those out, and half of that would be this is a 2.5. I can't read my writing. That's what the problem is. I'm going to use my calculator on that one because I'm late enough in the day and tired enough. The old brain is hurting. It's really hurting. Okay. If I can read my writing, that's 0.250. I'm just going to put 0.25. Calculator will take care of significant digits times 1.5, which is really 1.50, but the calculator will take care of it. That gives you 0.375 meters per second. Now, Let's see what else goes by that ratio of 1 to 2 or 2 to 1. Your final speeds do. Your accelerations do. Your final speeds do. The astronaut is moving twice as fast, but in the opposite direction as the spacecraft. Now, if they were really out in outer space and they weren't tethered to each other or something like that, and most of the time if they're working on something, they tether themselves to it. But if he were to push on the spacecraft without a tether, they're never going to come back again, because guess what? No air resistance, nothing. That motion keeps going opposite directions. He never get back in touch with that spacecraft. That's why they usually tether themselves to the thing they're working on. So if he does push on it, they move apart, then he can pull on it and they come back together about the same place they were before. Okay? So, but he moves away twice as fast as the spacecraft does, because he's got half the mass of the spacecraft. So that should be what we've got here. That velocity of the astronaut 0.750 meters per second, and the mass of the spacecraft of 0.375. I mean the velocity of the space, or speed I'll call it. Okay, and they gave that same formula we did, only they put the V initial at the end rather than the beginning. Okay, we've just gone over our time, but guess what? There'll be no extra charge today. Okay, now I think the lab is going to go pretty quickly. We'll start next time at momentum 2.7. Okay, let me make sure I don't have any other marks on this page. I don't see any. So therefore, seems like I should, but I don't. So that's where we'll begin next time. So what do we have to do from here on? We covered about 12 pages today, and we'll cover about 8 next time. So more than likely next time we will start on chapter 3. Okay, so let's take a quick break. I need one, folks. I really do. Let's try to keep it less than 5 minutes. I don't know for sure if I'll make that, but I'll do my best and come back in just about 5 minutes. And what I'll do is turn off the recording. I won't turn off Zoom. Okay, so hopefully we're still recording. Yeah, we are. And here's the screen share where we are now. I'm going to move this taskbar out of the way because it, again, is right in the way. If I could get it to come up. There it is. Okay. Yuck! Okay. Let me try this one. Okay. You can't see this, but it's a pain in the neck. The taskbar just gets in the way. Okay, now you can see my weekly activity. You probably could always see them. I couldn't because of the taskbar. I'm going to move y'all. You can't see who you are, but I'm going to move you to the top for right now so I can get to this. Weekly assignment and activities. Go over here to the down arrow, click on it, and we're in week 2 now. Click on that. Well, no. You only click once. Some things you double click. This one I double clicked and didn't do. The overview is still the same as it was. I added to instructional materials here Lab 3. That wasn't here before. So we're going to the same website, the HTTPS PHET Colorado, that's physics, whatever that stands for, online access. We're going back to there, but we're going to do the one for Lab 3, not the one for Lab 2. Remember, this is the one I made it as a file rather than copying the link. So that means I have to take this link and put it in the command line, whereas I would have just been able to click on it, copy that to the command line. The trouble is your names are in the way of the command line, so I don't know how long it is. I'm going to go all the way to the end, and hopefully I've got it knocked there. And paste. Okay, and then I'll click on that. So I'm going back to that. Okay, Now I got to move your names out of the way because I can't see where at. Here's the simulations, physics, just like before. Now, I'm going to do a timeout here. Let's go back to a screen share with well, I can't see it. It was the I guess the reason I'm in it. That's it. So I'm going to have to go back and open up again my PowerPoint. Sorry, this stupid Blackboard. It has all these layers in it, and sometimes you can't. And I'm going to have to minimize this. This is such a pain in the neck. Let me minimize this. I'm going to have to redo a lot of stuff here. So let's go back to this and do, this is what I'm looking for, employee portal. Okay, and my Blackboard. See, I was opening the other thing through Blackboard, so that's why I couldn't get back to it without closing that. Now I got to move you all back to the top again. This is such a pain in the neck. Okay, now I've got to find their class again. Way down here, you have a lot fewer classes, I'm sure, to look through than I do. There we are. That you double click on. This you single click on. This you double click on. Goodness gracious, this is taking forever. It's trying to open, but it's not opening. Okay, I'll close it. Let me open it this way. There it comes. Okay. Go back to instructional materials for week 2. This is so, there's got to be a better way. In fact, there is a better way, but they won't let us do it. Okay, so that's your HTTP. That's under this one, okay, this tab. So we'll come back to that in a minute. Here is the lab. For you to open it, you click on the 3 dots here. They call it the elliptical. Why they call it that, I don't know. When you click on that, it says download original file. If I were to click on that, you see the file start downloading here in the lower left corner, and when it gets fully downloaded, you click on it. I've already got it as a file, so I'm going to not download. I'm going to go to goodness gracious, yeah, right here. But it's not showing. Oh, here it is. Okay, there's lab 3. Now here's the problem with my lab 3. When I was doing it late last night, it was after 10 o'clock when I was finally getting to do it, because I was getting ready for my infusion this morning. Everything else was happening. I'm still dealing with the death of my friend and the cleaning out her apartment. I mean, the day was just terrible. It was wasted, all over the place. It says go to Blackboard page for this course. Yes. Go to course content. That's where we were. Now here I was doing a different form this summer. All you had to do was scroll down to laboratory at simulations and open them. That's all you had to do last summer. What you need to do, and you probably need to fill this in here, you go to course content, open up the weekly activities, then open up week 2 activities, and then open up the instructional materials. And then under instructional materials, you'll copy the lab simulation up to the command line, click on that, it opens. Now we're at the same place here. So you see so many more steps to where they're doing Blackboard in this new template form, which I find just totally irritating. Okay, there I had two commands, here I have 4 or 5. Okay, but if you do that, then that gets us to here. Now I'm going to make this a new share. Okay, and we're going to make this a new share. So let's go back to the document in Google Chrome. Nope, that's not the right one. I need the FET. It may be this one. Let's see if it's this one. No. Well, it's lost it now. Okay, so I'm going to go back here. Okay, I think I have to close this and then do, this is such a pain. New share. There it is. Now, all right, now we've got to simulations in physics. Okay, what we're looking for, I think, is something like forces. I had it open and now I can't remember what it is. Do any of you have it printed yet? I thought I had it. Forces in motion. Okay, let me see if I have it printed. I thought I did, but okay. No, I don't see it. Okay, I'll have to depend on you. I thought I printed it, but I don't see it. I think I just ran out of time. I think that's when Zoom stuck and I couldn't get out of Zoom to print it. That must be it. Okay, we're looking down for forces. I'll recognize it when I see it, I hope. Okay. It's pretty much alphabetical. Okay. Forces in motion. Basics. Is that what it said? That's the one we go to. So I'm going to click on that now. And it opens up. And rather than download, which I used to think you had to do, all you have to do is press on the start button, the triangle in the circle. And then it takes just a little while. And we're going to talk about net force. We're not going to do motion, friction, and acceleration. We may do that in a later lab, not now. We're doing net forces. That's what we've been talking about today. So click on the net force one. Okay, here's what you got. Now, you tell me. Now, let's see. I think I'm going to have to move y'all out of the way because, okay. I think it first asks for you to click these boxes. Is that right? Okay, let me go to my lab. In fact, I may go on and print this. Okay, let me go on and print this. Control P, I think it is. Let's see if that will print. I'm going to have to move y'all out of the way so I can read this. Okay, I think that's going to be a two-sided lab. Is that what you got? Yeah. So let's print it. I hope I'm in the right. Yes, I am. So hold on just a minute. I'll be right back. I'll put this on pause for a minute, but remind me to start this back. Okay, now we're back. I've got the lab printed. And remember the corrections at the top. It goes go to course content, and where it says scroll down to laboratory simulations, that's where you have to go to weekly activities, click on that, open it on the arrow on the side, then go down to week 2, click on that, and then go down to instructional materials, and then go down to and click on the same lab simulation link. You have to actually copy and paste it and click on it to get here, and then you have to also open the lab and preferably print it like I did here. All those many extra steps. Then click on simulations, then on physics, scroll down to forces and motion basics, and this is where we are. It says click on download. Okay, now I've got to, I think that's an extra step that I decided not to do anymore. Yeah. Okay. Now, you don't have to do the download anymore. Remember, now you can just do the triangle in the circle. So that should replace, click on download, click on the triangle in the circle. I'll try to work this up so it'll be correct, and then change the one that's there. That opens it. Click on it, it will open. Click on net force, that's where we are here. Click on sum of forces right up here. Click on that. Click on values. Click on that. It says click on speed. Click on that. Okay. Now, I think what this does, if you have the microphone on, you hear these little androids grunting and groaning. I don't find that particularly helpful. Okay. But I want you, it says drag a little blue android to one of the knots. So let's put them up here on that knot. Okay, and here's what you record: the sum of the forces. The little blue android can pull with a force of 50 newtons. Okay, and the direction is to the left. The sum of the forces is 50, the direction is to the left. Got it? Now, my question to you, will there be an acceleration? Yes or no? Okay, you're absolutely right. If there's a net force, sum of forces, you're going to have an acceleration. Okay? In what direction? To the left. Excellent, you got it. Record the motion of the cart. Now, that's going to take some effort on your part. Here's what you're going to be looking at. Okay? Of course, which direction it's going, we've already answered that, it's to the left. But look at the speed. Now, possibilities on the speed would be it stays at 0. I think we've decided it's not. Okay? It could move at a constant speed, not 0. Or it could be at an increasing speed. So that's what you're going to look at when it says record the motion of the cart. It moves with what type of speed in what direction. Okay, so I'm going to press go, and I didn't say that, and you see what's happening. Start slowly and increases its speed, right? Not very far, but it does. So it starts moving to the left at a very slow speed, but it's increasing constantly. That's an acceleration, folks. You just said it was going to do it. And how does the speed change? I think I just answered that. It starts slowly and speeds up to the left. Now we could call that, because they're calling this speed, not velocity, you don't have to put the sign with it. So it's increases, starts slowly, increases, moving to the left. Okay. Now, drag a little red android up to the knot. Okay? And when I say go, well, okay, before we do that, record the sum of the forces and the direction. What's the sum of the forces now? 0. Okay, because the little blue Android is pulling to the left with 50, the little red Android is pulling to the right with 50, and guess what? Net force is 0. Okay, what direction? No direction. Oh, wait. Ugh, that's a tough question. The net force has no direction, but that doesn't mean, okay, that there's no direction involved. What's the next question? Will there be an acceleration? No. Okay, so 0 acceleration, no direction. Okay, so click on go. I did have that before, I just didn't see it. What do you think is going to happen? Is it going to stay steady? Remember, it was moving. I just paused it. It was moving, and since there's no acceleration, it's going to continue moving to the left, but this time at a constant speed. So see, when I go, the speed doesn't change. Notice it was the same speed all along. The speed changed with just the blue Android pulling. When they had a net force of 0, acceleration of 0, the speed was constant. So how does the speed change? I think I just changed it. Said it. It doesn't change. The speed is constant to the left. Okay. Now what I'm going to do now is pull a second little red Android. Now if I'm going too fast, stop me, folks. Say slow down. Let me get this written. Okay. Is there something I need to go back and repeat? Well, the force has no direction. Okay, that's right. Will there be an acceleration? No, no direction for acceleration because there is no acceleration. But the next one, what is the motion of the cart? The cart still has motion because it was still going to the left, but now it's not at an increasing speed like it was without the little red Android. It's got a constant speed. So the speed has a direction, the velocity has a direction, the forces and the accelerations have no direction. Okay. And how does the speed change? It doesn't. It's constant. Okay. Can we go on to the number 4? No, number 3. Number 3. Drag a second little red Android up to a knot. Okay. And answer the same question. Is there a sum of forces now? What? Okay, sum of forces. 50. You have 100 to the right, 50 to the left. That adds to, because forces are vector quantities, you don't add the total, you add in which direction. That's 50 to the right. Okay, so the direction is right. Will there be an acceleration? Which direction? To the right. Does that mean the car is going to immediately move to the right? No, it's still going to go to the left, but at a decreasing speed because its acceleration is to the right. So let's see if that happens. Okay, I'm going to press go. Slow down, slow down, slow down. Uh-oh, I didn't allow it. Blue wins. Let's reset. Okay, I left it going too long for you. So I'm going to put I'm just going to get back where we were. Okay, I think what I'll do this time is let him pull a little bit further. Whoops. Go. I'm just repeating what we've done. Constant speed there. What happened to my speed? Oh, all these. I'm sorry. All right. Now, I pull the second little Android. See, I let that speed get too great. So now I press go. This is where we pick up with 3 under record the motion of the cart. It starts off going to the left at that speed, whatever that is, but it slows down, and then starts increasing to the right. Okay? So record the motion of the cart. Begins going to the left, but at a decreasing speed, which that's an acceleration to the right. The speed decreases, and then when it stops, it slowly starts increasing to the right until it gets to that speed there. Okay? Let me know when you've got all that written. Angelita, are you loving this one? Good, excellent. Not quite as many calculations to make, huh? Okay, let me know when we're ready. Good. She was good last summer in the Physical Science 111 course. Wasn't that when you were in it, Valerie, or was that in the spring? Summer, okay. Okay. These are a little more involved than the summer labs were. Okay. Okay. Can I move the second little number 4, second little blue android to the knot? Ready? Anyone still need a little more time? Okay. Okay. Take your time. Now, I may have let the speed get too great, but we'll see. Okay. Everybody else ready? Okay. Gonna move the second little blue android up to the knot. Okay. What's the sum of forces? What's the direction? No direction. Exactly. What's the, will there be an acceleration? Really? Say that again. There is no acceleration. If there's no net forces, there's no acceleration. So does that mean there's no speed? That's the question you were answering. Yes, there continues to be a speed, but it's going to be a, what kind of speed? Constant speed, because there's no acceleration. Acceleration is a change of speed. If you don't have an acceleration, you have a constant speed. This has a speed. It's not going to accelerate. It's going to keep at that speed. So let's see if that happens. So I'm going to press go. I'm not going to leave it too long. Tell me what happens. Moves to the right at a constant speed. That speed did not change on the dial any. Okay? How does the speed change? It doesn't. It continues to the right at a constant speed. Who's next? Medium blue. Okay, let me know when you're ready for medium blue. Okay. Everybody else? Okay. No, you're good. Are you ready? Okay, never mind. Are you good and ready? Okay, never mind. So let's move medium android up to that knot. Okay. What's your sum of forces now? 100. So whereas the little androids were 50 Newton, they could pull that kind of force. Medium pulls with 100. So what's the net force? Net sum of the forces? 100 newtons to the left, so that's your direction. Will there be an acceleration? Yes, there will. Which direction? To the left. Now, we don't know the masses of the androids, or we could actually calculate the accelerations. We don't know it, so we're not going to. So, you tell me what you think is going to happen when I click on go. Does that mean it's going to start moving to the left? Because that speed was to the right, but what's the speed going to do? Okay, yeah, okay. It's going to start at that speed, but slow down as it goes to the right because the acceleration's in that direction, the left. So finally, it's going to hopefully come to a stop before we hit the bumper here, like we did last time. And if that's the case, then it will stop and then start speeding up to the left. You agree? Let's see. Okay, so record the motion of the cart. I'm going to press go. Now you can go back and play with it yourself. I've shown you how. Let's do it. Go. Decreasing speed, decreasing speed. Came to a stop. Increasing speed to the right. Stop, 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 stop. Okay. Okay, I hit the button twice. Sorry. So, I shouldn't have done that. I'm going to have to be really careful next time. So record the motion of the cart. Now the whole motion. It started to the right at a decreasing speed, came to a stop, and started at a slow speed going to the left, but started increasing its speed because the acceleration was to the left. Okay? Now, how does the speed change? Decreasing speed to the right, stopped, increasing speed to the left. Because it is an acceleration, the speed, since it's a straight line motion, is always changing. If there's an acceleration. If there's no acceleration, speed doesn't change. So, medium red, ready? Everybody? Need a little more time? Okay, medium red going up to that knot. Okay, what's the sum of the forces? Okay, how about the direction? No direction, because there's no magnitude. What's the, will there be an acceleration? No. What direction? None, because it has no acceleration. So, what do you think the cart's going to do? No. When we stopped it before, it had a speed to the left in that direction. It's going to continue there, but not going to change, because an acceleration is a change of velocity or change of speed. Since it has a zero acceleration, the speed's going to remain constant. That's another definition of uniform motion. No acceleration, speed doesn't change. Whether it's stopped or whether it's going, the speed doesn't change. I'm not going to let it go long, but notice that the speed doesn't change. Still the same. Didn't change at all. Okay. Motion of the cart continued to the left. How did the speed change? It didn't. Stayed at the same speed because there's no net force. And with no net force, you have no acceleration. Acceleration is the only thing that's going to make the speed change. Big red. Are y'all ready for them or not? Okay, let's get big red up there to the last knot. What's the sum of the forces? Okay, in what direction? To the right, to the right. Okay. Now you see the sum is totally, he was 150, this one was 100, that's 250, and two more 50s made it 350. Over here you only got the 100 and the 250, so that's 200, so the net force is to the right 150 newtons. Okay? Now, when I click on go, what do you expect the motion of the cart to do? Right off the top? we're accelerating, but the speed was going to the left, so that right acceleration, did we answer that question? Will there be an acceleration? Yes, in the direction, same as the sum of forces to the right. But the speed was to the left here, remember? So that speed's first got to decrease in speed, come to a stop, and then start moving to the right and start increasing in speed. Follow? That's A. Okay. Okay, we haven't done it yet, but here's what we expect to happen. The speed was going into the left at a pretty high rate of speed. I'll let it get too fast. Okay? So it's got this, because the acceleration's to the right, that speed's got to decrease and go to zero, come to a complete stop, and then at a slow rate start moving back to the right, increasing the speed as you go, because there's a net force, and that force gives you a net acceleration. Acceleration gives you a speed change to the right. That starts being decreasing speed to the left, then increasing speed to the right. Okay? So let's see if that happens. You ready for go? Okay. Decrease it. Oh, just stopped right at the moment, right? And starts increasing to the left again. I mean, to the right again. Whew, barely got that one to work. Okay. Record the motion of the cart. Started to the left because it had a speed in that direction, but was slowing down to the left, then came to a complete stop and started moving to the right. So the speed decreased to the left, stopped, increased to the right. Net force to the right, net acceleration to the right. That's why it happened. Now, Big Blue, are y'all ready for them or not? Take a few more minutes or move Big Blue. I'll go on and move him, but I won't start it until, well, no, I'll wait. Are y'all still writing? Okay. So let's get Big Blue up there on that last knot. What's your sum of forces? 0. What's the acceleration? Okay, in which direction? No direction. Okay. What's the, will there be an acceleration? Really? Sum of forces 0? That means the acceleration 0. And what does that tell you about the speed? No speed change. Acceleration makes a speed change. So since the speed was going pretty fast to the right, guess what it does? Continues pretty fast to the right, but doesn't change its magnitude. Okay? In what direction? No acceleration, no direction. Okay? Speed is to the right, but no change of speed. Let's see if that works. Never changed, did it? Continue to the right at the same speed. Why? Because there was no net force. With no net force, there's no acceleration. With no acceleration, the speed does not change. Even though you had the same forces on both sides, it doesn't change the speed. That's the key. Now, question. Yeah, sum of forces was 0. There were lots of forces, but the sum of forces, the net force, was 0. You had 350 to the right, but 350 to the left. Sum of the forces, 0, because this is a plus, that's a minus, they add the 0. Okay? Direction, with none, because with no speed, you can't, with no force, you can't have a direction. Will there be an acceleration? I know there was a speed to the right, but not an acceleration. If there's no net force, there is no acceleration. Newton's second law, F equal ma. If there's no net force, there's zero acceleration. Mass, you know there's masses. We don't know what it is, but they all have masses. So the mass can't be zero. It has to be that the acceleration is zero. What is acceleration? Change of velocity, which means change of speed. And since it was going to the right at the beginning, it's going to continue going to the right at the same speed because it's not accelerating. Right? Got it. Okay. So if there's no acceleration, there is no direction for the acceleration. So when we clicked on go, what was to record the motion of the cart? To the right, to the right, to the right, right, right. Does the speed change? No. It stayed at the same speed because there was no acceleration. No net force acting on it. It's going to continue moving. Newton's first law. If there's no net force, no unbalanced force, it's going to keep moving. Straight line motion, same speed. Now, number 9. Are y'all ready for 9? Okay. What is the relationship between the sum of forces to the acceleration? If there's a sum of force, it's either going to be to the right or left. Therefore, you'll have an acceleration either to the right or left. So the relationship would be the acceleration is in the same direction proportional to the amount of the force. Not equal to the amount of force, but proportional to it. The constant of proportionality is your mass. And we were changing masses always. But the sum of forces will be in the same direction as or the acceleration in the same direction as the sum of forces, proportional to the magnitude of that sum of forces. If it was zero, the acceleration was zero. So what's the relationship between the sum of forces to the speed? That's a little bit tougher, but still I think it's doable. If the sum of the forces, where do you want to start? We can do left, right, or zero. Okay, zero first. If the sum of forces was zero, what can you tell me about the speed? Yes, exactly. The speed is constant. It doesn't change. If the speed was zero, it stays zero. If the speed was to the right, it stays to the right at the same magnitude. If the speed was to the left, it stays at the same magnitude to the left. It does not change. That's all you have to say. The speed doesn't change if the sum of forces was zero. Now, the next one, what if the sum of forces was to the left? Okay, now you don't have to write all these down, but I want you to think them. If the initial speed was to the right, but the sum of forces to the left, what's that speed going to do? Slow down, stop, and then start increasing to the left. Isn't that where we had it? Yeah, increasing to the left. You're absolutely right. Now, if that speed was not going to the right to begin with, and your net force is to the left, then the speed increases to the left. Not at a constant speed, but an increasing speed to the left. You don't have to write all that down, but just get in your brain what's going to happen there. And then it's just the reverse if it's net forces, sum of the forces was to the right. If the speed was originally to the left, it's going to slow down, stop, and then gradually speed up to the right. But if the sum of the forces to the right and the speed was not to the left, it's just going to increase to the right. So, good deal. Does this sort of explain or illustrate what we're talking about with forces? Okay, good deal. Now, that was, though there are only 10 questions here, lots of them have multiple parts. 1, 2, 3, 4, 5, 6. 6 parts for most of them. Yeah, your test is going to be mostly multiple choice, a lot like it was in, see, that first test had more calculations on it. I told you that ahead of time. Yeah. Well, that's because the test bank for that first chapter was pathetic, and it had nitpicky points. I had to rearrange it so it was something you could really do. I'm not sure I could have answered the ones they had in the test bank because I couldn't tell what point they were trying to make. Okay, so rather than be confusing to you, I tried to just write it as problems. Okay, now all the rest of the test, chapters 2, which we're in now, chapter 3, which we're going to, 4, which we're going to, 6, which we're going to, and 8, which we're going to, are going to be more like your Physical Science 111 test, more multiple choice, though there will be probably 1 or 2 calculations, pretty simple calculations, on each of the tests, and maybe a few fill in the blanks like you used to have in 111. That first test was the one that was more calculations, only a few multiple choice, and quite a few fill in the blanks. That hey, no. Okay. Yeah, that was the only test that's going to look like that. Then the final exam will be a lot like your final in the other class. It's going to be matching. Probably one of the easier tests you have. Uh, I have to have everyone turn it in before we do, but then when everyone turns it in, absolutely, I want to go over it. The trouble is, I don't know why, but traditionally, there's always not the same people, but 1 or 2 people who have not turned in, say, the first test. Maybe 1 or 2 haven't do the first lab. Not the same ones, and then the second lab. And it gets up, and it usually winds up, in fact, what I was doing while I was waiting for my infusion, I had to wait at least an hour or close to an hour this morning. I was out there grading papers. And I was grading papers from 111 where the students had incompletes. And because they hadn't turned in their work, I couldn't share the whole test with the whole class. So get your classmates to turn in their test, okay? As soon as they do, then we can go over the test, okay? Now, that also creates an issue. Look at today. We have maximum of 10 out of 16 people here. So how are those other 6 people going to do their labs? Well, I'm recording it. It'll be on Blackboard, on YouTube videos sometime late tonight or in the morning, probably in the morning. Except I can't move it in the morning because I'll be at the infusion lab. But when I get home tomorrow afternoon or sometime Saturday, I don't know when, I'll get it over into the, infusion lab. I mean, goodness gracious, into YouTube video. And then in Blackboard, you can access that. But you can go to the one we did this last spring. It's out there. Now, last spring, this was lab 3. No, I'm sorry, lab 4. Yeah. And I couldn't find anything to replace the lab 3 last time, so I went on and made this lab 3 here. So we're going to have plenty of labs to choose from in the future. The energy has several chapters on several labs that I think we can fiddle with. So, but this one was already done, and I only had 30, 40 minutes to work on it. And like I said, I forgot to change the directions at the top. But the rest of it was in pretty good shape, so I just used this one. All right, any questions on any of those? Only 10 questions, but many of those questions have, in fact, most of them have 6 parts. 8 of those have 6 parts each. 1, 2, 3, 4, 5, 6. So 8 times 6 is 48, 49, 50. There's a total of 50 blanks here. So each blank is worth half a point. So do the best you can. Any question? Anybody? Do you need to see any of it redone? Did I go too fast? Did you not understand what I'm saying? No. And again, if you want to do it yourself, play with it. That's why I put the link out there. Okay? But you can just go to YouTube and follow what we did. Is this making the labs too easy? Or are you learning something from the lab when we do it this way? Okay, good deal. All right, good answers anyway. Okay. All right. Excellent. Right. Are you still at work? Oh, okay. Oh, I see. Right. Right. Okay. Right. And then later, if you could get on your computer or maybe even your cell phone and see the lab, that might make it more sense. So, all right. That's why I give you at least a week to turn in the lab. Now, some people are behind on that too, but try to get your test and your labs done within a week, but take the time to get them right. I don't want you to turn them on impartial and lose points. I want you to get the most points you can. But don't get too far behind, please. But the labs are going to come fast and furious, even as fast or faster than 111 did. It's just the tests aren't going to come as fast and furious. That first one was pretty quick, but this one's going to be another class period before, and we'll finish that next time on Tuesday and hopefully do the third lab. Now I've got to work one up for that. I think it'll probably be on momentum if I can find a good momentum lab on here. I can't remember if we did one last spring. It's just too long ago. If I've got it, then that's going to be easy. If I don't have it, I've got to make it up. But I hope to be able to use the weekend to do that. But all this stuff with the death of my friend and me being in charge of everything with that, and then having treatments this week, and I'll just have no energy whatsoever. It's running me down. Like yesterday, I had to go over and let a bunch of people into her apartment. Most people I've been around since COVID hit. My wife got really mad at me. I didn't know there were going to be that many people there, but I just had no energy to do anything. I just tried to stay away, as far away as I could from all the people in a small apartment. So it was not easy. And we all had masks. Everybody was trying to be safe, but it just was frustrating. And I just had no energy to do much of anything. So it wore me out. And then I had treatment today, which wore me out. And I'll have more treatment tomorrow, which is going to wear me out worse because today was only 10%. And there was a period today, about an hour or two into when they had started the treatment, I was getting hot. Just hot all over. I could tell, my wife says I'm sort of crazy, I could tell there was a battle going on in my blood, you know, that the monoclonal antibody was attacking the white cells and tearing them apart, and I was getting hot, and I just asked for a cup of ice. They brought it to me. It was nice crushed ice, so I would just take the ice and hold it on the roof of my mouth, just trying to make me not feel as hot. And it took me about a third of the cup, doing that slowly, let it melt slowly, and it finally started feeling a little better. But I was afraid I was going to be sick or something. And I didn't want that to happen, and they're going to stop everything and maybe give me more drugs or something. I said, the ice will work. I won't tell them I'm hot. Just give me some ice. And they did. They're really nice. So tomorrow's going to be worse than that, I'm afraid, because it's going to be a 90% dosage. So I'm going to be eating lots of ice tomorrow, I'm afraid, and they probably will slow things down very, very slow. Today I was out of there in less than 8 hours. Tomorrow it's going to be 8 hours or more. But they're not starting till 8:15, so that's going to be 4:30, 4:45, 5 o'clock. And if they don't have it all done, they're going to stop it at 5, I think, and then I won't get a full treatment. So that'll be their choice. That's why I don't like them to stop, because then they don't give me a full treatment. So anyway, that's my sad story. But any questions? That's what I said. I don't know when I'll get around to uploading this to Blackboard, because tomorrow when I come home, I'm going to bed. I felt like a little bit like doing that today, but I knew I want to get this class in. That's one reason I've been drinking Coke and things, just getting my energy up. I'm feeling much better now. Okay, but it was sort of touch and go at the beginning, but I'm feeling much better. But tomorrow, nope. If this thing hasn't uploaded by the time I go to bed tonight, it's going to be sometime. If not tomorrow night, it's going to be Saturday sometime. I'm going to try to take it easy this weekend. It's supposed to be a beautiful weekend, and I hate to be sleeping it away, but if I need to, I'm going to. All right, anyone need any more physical science? Okay. All right, to stop the sharing, if y'all don't want to see any more of it. You okay? Okay. Then I'll end the meeting for everybody. I'm cheating you out of, what is it, about 45 minutes of your tuition dollars. I know you're going to write the president and tell her I'm not giving you a fair shake here. Thank you, Valerie. She's my enforcer. Okay, good deal. Okay, take care, folks. We'll see you next week. Be safe this weekend. Bye-bye.